Testing my mic here. Alright, and we are live. So, as always, I'm gonna continue with my with me streaming what I learned, and today we're gonna continue our Pytorch course by Daniel Bock. Let me mute my secondary monitor. With that, overlaid quite a bit. Should be fine. Let us begin. Alright, so let me take out the course here. Why can I? Hello? Oh, I haven't muted my YouTube yet. That's the reason. That should be better. All right, let's go to the segment we last left off. We were doing multi-class classification. Multi-class classification? I guess there's two classes in it. And yeah, we left off at that point, so let's just take that back. So that should be using an okay, we finished that. Loss optimizer.
If you're a web designer, here are 4 Wix Studio features you gotta know.
Welcome back. So over the past few videos, all depending on the data set that you
Let's see where we have coded and just try to back. I think we started a new Python notebook, didn't we? Yeah, it's we started untitled 2.ipynb. We set up the loss function and optimizer, so
you're working with will depend on what in Pytorch
skip a bit.
and optimizer. Now here comes the question. If we're working on classification, previously we used, let's go to the next one. So you use predicting and a little bit of
It's this,
again
segment, all right. Let's just
this is problem specific, but with a little bit of practice, you'll get used to using different ones. So, for example, for regression, you might want, which is regression's predicting a number. And I know it can get confusing because it looks like we're predicting a number here. We are essentially predicting a number, but this relates to a class. So for regression, you might want MAE or MSE, which is mean absolute error, or mean squared error. And for classification, you might want binary cross entropy or categorical cross entropy, which is sometimes just referred to as cross entropy. Now, where would you find these things out? Well, through the internet, of course. So you could go, what is binary cross entropy? I'm going to leave you this for your extracurriculum to read through this. We've got a fair few resources here. Understanding binary cross entropy / log loss by Daniel Godoy. Oh, yes. Great first name, my friend. This is actually the article that I would recommend too if you want to learn what's going on behind the scenes through binary cross entropy. For now, there's a lot of math there. We're going to be writing code to implement this. So Pytorch has done this for us. Essentially, what does a loss function do? Let's remind ourselves. Go down here. As a reminder, the loss function measures how wrong your model's predictions are. So I'm also going to leave a reference here to, I've got a little table here in the book version of this course, so 0.2 neural network classification with Pytorch, set up loss function and optimizer. So we've got some example loss functions and optimizers here, such as stochastic gradient descent or SGD optimizer. Atom optimizer is also very popular. So I've got problem type here, and then the Pytorch code that we can implement this with. We've got binary cross entropy loss. We've got cross entropy loss, mean absolute error, MAE, mean squared error, MSE. So you want to use these two for regression. There are other different loss functions you could use, but these are some of the most common. That's what I'm focusing on, the most common ones that are going to get you through a fair few problems. We've got binary classification, multi-class classification. What are we working with? We're working with binary classification, so we're going to look at torch.nn BCE, which stands for binary cross entropy, loss with logits. What the hell is
I think we can skip a bit because we had already covered this portion.
However, Pytorch has many built-in options. So if we have .nn, what do we have in here? Loss functions. There we go. Beautiful. That's what we're after. L1 loss, which is MAE, MSE loss, cross entropy loss, CTC loss. All of these different types of loss here will depend on the problem you're working on, but I'm here to tell you that for regression and classification, two of the most common of these. See, this is that confusion again. BCE loss, BCE with logits loss. What the hell is a logit? My goodness. Okay, that's enough. And optim, these are different optimizers. We've got probably a dozen or so here. Algorithms. Outer delta, outer grad. I don't know. This can be pretty full on when you first get started, but for now, just stick with SGD and the atom optimizer. They're two of the most common. Again, they may not perform the best on every single problem, but they will get you fairly far just knowing those, and then you'll pick up some of these extra ones as you go. But let's just get rid of all of, maybe we'll, so I'll put this in here, this link. So we'll create a loss function. For the loss function, we're going to use torch.nn.bce with logits loss. Woohoo, this is exciting. For more on what binary cross entropy, which is BCE, a lot of the abbreviations in machine learning and deep learning is, check out this article. And then for a definition on what a logit is, we're going to see a logit in a second in deep learning, because again, deep learning is one of those fields of machine learning which likes to be a bit rebellious, you know, likes to be a bit different from the pure mathematic type of fields and statistics in general. It's this beautiful gestalt-ism. And for different optimizers, see torch.optim. But we've covered a few of these things before. And finally, I'm going to put up here, and then for some common choices of loss functions and optimizers. Now, don't worry too much. This is why I'm linking all of these extra resources. A lot of this is covered in the book. So as we just said, set up loss function optimizer. We just talked about these things, but I mean, you can just go to this book website and reference it. Oh, we don't want that. We want this link. Come on, Daniel, you can't even copy and paste. How are you supposed to code? I know I've been promising code this whole time, so let's write some. So let's set up the loss function. What did we say it was? We're going to call it LOSSFN for loss function, and we're going to call BCE with logits loss. So BCE with logits loss, this has this built in. Activation is implemented to the architect here. Find tables to have limitations. Did I find, and then loss? Just literally all numeric into one layer. We take advantage of the we're going to see the difference between them later on, like in the flesh. Just set the print loss. We'll see the same classification. So true now as our head tables. Divide a training loop, which we divide a single value in Python, and then we're going to calculate the accuracy. ACC stands for accuracy, equals correct, divided by the length of samples that we have as input, and then we're going to times that by 100, and then return the accuracy. Wonderful. So we now have an accuracy function. We're going to see how all of three of these come into play when we write a training loop, which we might as well get started on the next few videos, hey? I'll see you there. Welcome back. In the last video, we discussed some different loss function options for our classification models. So we learned that if we're working with binary cross entropy or binary classification problems, we want to use binary cross entropy. And Pytorch has two different types of binary cross entropy, except one is a bit more numerically stable. That's the BCE with logits loss, because it has a sigmoid activation function built in. So that's straight from the Pytorch documentation. And that for optimizer-wise, we have a few different choices as well. So if we check out this section here, the Pytorch book, we have a few different loss functions and optimizers for different problems and the Pytorch code that we can implement. But the premise is still the same across the board of different problems. The loss function measures how wrong our model is. And the goal of the optimizer is to optimize the model parameters in such a way that the loss function goes down. And we also implemented our own accuracy function metric, which is going to evaluate our model's predictions using accuracy as an evaluation metric rather than just loss. So let's now work on training a model. So what should we do first? Well, do you remember the steps in a Pytorch training loop? So to train our model, we're going to need to build a training loop. So if you watch the video on the Pytorch, so if you can Google unofficial Pytorch song, you should find there we go, the unofficial Pytorch optimizer.
You know what, as a refresher, let's just view the song once more. Although I'm pretty sure Daniel will sing it soon. Anyways, but let's just do it. So unofficial Pytorch optimization loops.
Expand your business and stay ahead. Use real-time data to forecast delivery routes. With AWS, businesses can push the boundaries of innovation.
Phone. I'm learning about burn a val loop. Me remember and forget. Train. So let's train. For an epoch in a range, Comauto.train, do the forward pass, calculate the loss, optimize a zero grad, loss backwards, optimize a step, step, step. Let's test. Comauto.eval with torch inference mode, do the forward pass, calculate the loss, print out what's happening. Let's do it again, again. For another epoch, Comauto.train, do the forward pass, and calculate the loss, optimize a zero grad, loss backwards, optimize a step, step, step. Let's test. Comauto.eval with torch inference mode, do the forward pass, and calculate the loss, print out what's happening. Let's do it again. for another epoch. Commodore train. Do the forward pass, calculate the loss, optimize a zero grad, loss backward, optimize a step, step, step. Let's test. Commodore val with torch inference mode. Do the forward pass, calculate the loss, print out what's happening. Keep going if you want, but don't forget to save, save, save.
Loop song. We're not going to watch that. That's going to be a little tidbit for the steps that we're going to code out, but that's just a fun little jingle to remember these steps here. So if we go into the book section, this is number 3, train model, exactly where we're up to here. But we have Pytorch training loop steps. Remember, for an epoch in a range, do the forward pass, calculate the loss, optimize a zero grad, loss backward, optimize a step, step, step. We could keep singing this all day. You could keep reading those steps all day, but it's better to code them. But let's write this out. So forward pass, 2, calculate the loss, 3, optimize a zero grad, 4, what do we do? Loss backward, so back propagation. I'll just write that up in here, back propagation. We've linked to some extra resources if you'd like to find out what's going on in back propagation. We're focused on code here, and then gradient descent. So, or optimize a step. So build a training loop with the following steps. However, we've kind of mentioned a few things that need to be taken care of before we talk about the forward pass. So we've talked about logits. We looked up what the hell is a logit. So if we go into this Stack Overflow answer, we saw machine learning. What is a logit? How about we see that? We need to do a few steps. So I'm going to write this down. Let's get a bit of clarity about us, Daniel. We're kind of all over the place at the moment, but that's all right. That's the exciting part of machine learning. So let's go from going from raw logits to prediction probabilities to prediction labels. That's what we want. Because to truly evaluate our model, we want to, so let's write in here, our model outputs are going to be raw logit. So that's the definition of a logit in machine learning and deep learning. You might read some few other definitions, but for us, the raw outputs of our model, model 0, are going to be referred to as logits. So then model 0, so whatever comes out of here are logits. So we can logits. So then model 0, so whatever comes out of here are logits. So we can convert these logits into prediction probabilities by passing them to some kind of activation function, e.g. sigmoid for binary cross-entropy and softmax for multi-class classification. I've got binary classification. I have to sound it out every time I spell it. For binary classification. So classification. So we're going to see multi-class classification later on, but we want some prediction probabilities. We're going to see what they look like in a minute. So we want to go from logits to prediction probabilities to prediction labels. Then we can convert our model's prediction probabilities to prediction labels by either rounding them or taking the argmax. So round is for binary classification and argmax will be for the outputs of the softmax activation function. But let's see it in action first. So I've called the logits are the raw outputs of our model with no activation function. So view the first 5 outputs of the forward pass on the test data. So of course our model is still instantiated with random values. So we're going to set up a variable here, y logits, and model 0, we're going to pass it the test data. So x test, not text, to device, because our model is currently on our CUDA. device, and we need our test data on the same device or target device. Remember, that's why we're writing device agnostic code, so this would work regardless of whether there's a GPU active or not. Let's have a look at the logits. Oh, okay. Right now, we've got some positive values here, and we can see that they're on the CUDA device, and we can see...
Although, do we have the... Oh, I need to define everything again, don't I? Let's run on. There we go.
They're tracking gradients now. Ideally, we would have run torch.inference mode here, because we're making predictions, and the rule of thumb is whenever you make predictions with your model, you turn it into a val mode. We just have to remember to turn it back to train when we want to train, and you run torch.inference mode. So we have a very similar setup here, we just don't have the gradients being tracked anymore. Okay, so these are called logits. The logits are the raw outputs of our model without being passed to any activation function. So an activation function is something a little separate.
That should not track the gradients anymore, and there we go.
The raw outputs of our model without don't have the gradients being tracked. We just have to remember to turn it back to train when we want to train, and you run torch.inference mode. So we get a very similar setup here, we just don't have the gradients being tracked anymore. Okay, so these are called logits. The logits are the raw outputs of our model without being passed to any activation function. So an activation function is something a little separate from a layer. So if we come up here, we've used layer. So the neural networks that we start to build and the ones that you'll subsequently build are comprised of layers and activation functions. We're going to make the concept of an activation function a little bit more clear later on, but for now, just treat it all as some form of mathematical operation. So if we were to pass the data through this model, what is happening? Well, it's going through the linear layer. Now, recall, we've seen this a few times now, torch and then linear. If we pass data through a linear layer, it's applying the linear transformation on the incoming data. So it's performing this mathematical operation behind the scenes. So y, the output, equals the input x multiplied by a weight tensor, a, this could really be w, which is transpose, so that this is doing a dot product, plus a bias term here. And then if we jump into our model state dict, we've got weight and we've got bias. So that's the formula that's happening in these two layers. It will be different depending on the layer that we choose, but for now we're sticking with linear. And so that the raw output of our data going through our two layers, the logits, is going to be this information here. However, it's not in the same format as our test data. And so if we want to make a comparison to how good our model is performing, we need apples to apples. So we need this in the same format as this, which it's not, of course. So we need to go to a next step. Let's use a sigmoid. So use the sigmoid activation function on our model logits. So why are we using sigmoid? Well, recall.
Well, I'm trying to guess here, but from memory, I think sigmoid just compresses whatever value we give it and turns it between -1 and 1 or 0 and 1 or something. So I think that's what he's doing.
In a binary classification architecture, the output activation is the sigmoid function here. So now let's jump back into here, and we're going to create some pred probs. And what this stands for on our model logits to turn them into prediction probabilities. Probabilities. So y pred probs equals torch sigmoid y logits. And now let's have a look at y pred probs. What do we get from this? Oh, well, we still get numbers on a page.
Oh. Well, they are between the... Maybe it did get applied or maybe it didn't. Let's check what happened.
Goodness gracious me. But the important point now is that they've gone through the sigmoid activation function, which is now we can pass these to a torch.round function. Let's have a look at this. Torch.round, and what do we get? Pred probs. Oh, the same format as what we've got here. Now you might be asking, like, why don't we just put torch.round here? Well, that's a little, this step is required we can't just do it on the raw logits. We need to use the sigmoid activation function here to turn it into prediction probabilities. And now what is a prediction probability? Well, that's a value usually between 0 and 1 for how likely our model thinks it's a certain class. And in the case of binary cross entropy, these prediction probability values, let me just
that's what sigmoid does. I think it's confirmed.
Write this out in text. So for our prediction probability values, we need to perform a range style rounding on them. So this is a decision boundary. So this will make more sense when we go y pred probs. If it's equal to 0.5 or greater than 0.5, we set y equal to 1. So y equal 1. So class 1, whatever that is, a red dot or a blue dot, and then y pred probs. If it is less than 0.5, we set y equal to 0. So this is class 0. You can also adjust this decision boundary. So say if you wanted to increase this value, so anything over 0.7 is 1 and below that is 0. But generally, most commonly, you'll find it split at 0.5. So let's keep going. Let's actually see this in action. So how about we recode this? So find the predicted probabilities in, so we want the predicted labels. That's what we want. So when we're evaluating our model, we want to convert the outputs of our model. The outputs of our model are here, the logits. The raw outputs of our model are logits. And then we can convert those logits to prediction probabilities using the sigmoid function on the logits. And then we want to find the predicted labels. So we go raw logits, output of our model, prediction probabilities after passing them through an activation function, and then prediction labels. This is the steps we want to take with the outputs of our model. So find the predicted labels. Let's go in here. A little bit different to our regression problem previously, but nothing we can't handle. Torch round, we're going to go y pred probs. So I like to name it y pred probs for prediction probabilities and y preds for prediction labels. Now let's go in full if we wanted to. So y pred labels equals torch.round, torch.sigmoid, so sigmoid activation function for binary cross entropy, and model 0 xtest.to device. Truly this should be within inference mode code, but for now we'll just leave it like this to have a single example of what's going on here. Now I just need to count 1, 2, there we want. That's where we want the index. We just want it on 5 examples. So check for equality, and we want print torch equal. We're going to check y preds dot squeeze is equal to
why can't I hit an equal symbol there? Yeah, there you go.
YPred labels. So it's just, we're doing the exact same thing. And we need squeeze here to get rid of the extra dimension that comes out. You can try doing this without squeeze. So get rid of extra dimension once again. We want YPreds dot squeeze. Fair bit of code there, but
let's just see what we did then. So first thing we called in the my predictions is torched around by probability. Okay.
this is what's happened here. We create YPreds. So we turn the YPred probs into YPreds. And then we just do the full step over again. So we make predictions with our model. We get the raw.
Oh, okay. It's just he just combined all the steps together. So what we're doing is we're making the predictions. Here we go. Then we are calculating the probability using torch.sigmoid. And then we are getting our labels.
Or logits. So this is logits to pred probs to pred labels. So the raw outputs of our model are logits. We turn the logits into prediction probability.
Let's write that comment down. What we did here is we converted logits, that is the output of our model, raw output of our models, into probabilities, prediction probabilities, which were then converted into prediction labels.
Probabilities using torch sigmoid, and we turn the prediction probabilities into prediction labels using torch.round, and we fulfill this criteria here. So everything above 0.5, this is what torch.round does, turns it into a 1. Everything below 0.5 turns it into a 0. The predictions right now are going to be quite terrible because our model is using random numbers, but YPreds found with the steps above is the same as YPred labels, doing them all in one hit, thanks to this check for equality using torch equal YPreds.squeeze, and we just do the squeeze to get rid of the YPred labels, doing them all in one hit, thanks to this check for equality using torch equal YPreds.squeeze, and we just do the squeeze to get rid of the extra dot label because torch.round does, turns it into a 1, everything below 0.5 turns it into a 0. The predictions right now are going to be quite terrible because our model is using random numbers, but YPreds found with the steps above is the same as YPred labels, doing them all in one hit, thanks to this check for equality using torch equal YPreds.squeeze, and we just do the squeeze to get rid of the extra dimensions, and we have out here some labels that look like our actual Y test labels. They're in the same format, but of course they're not the same values because this model is using random weights to make predictions. So we've done a fair few, and we have out here some labels that look like our actual Y test labels. They're in the same format, but of course they're not the same values because this model is using random weights to make predictions. So we've done a fair few steps here, but I believe we are now in the right space to start building a training and test loop. So let's write that down here, 3.2, building a training and testing loop. You might want to have a go at this yourself. So we've got all the steps that we need to do the forward pass, but the reason we've done this step here, the logits, then the pred probs and the pred labels, is because the inputs to our loss function up here, this requires, so BCE with logits loss requires what? Well, we're going to see that in the next video, but I'd encourage you to give it a go at implementing these steps here. Remember the jingle for an epoch in a range, do the forward pass, calculate the loss, which is BCE with logits loss, optimize the 0 grad, which is this one here. Do the forward pass, calculate the loss, which is BCE with logits loss, optimize the 0 grad, which is this one here. Loss backward, optimize a step, step, step. Let's do that together in the next video.
Wait, let me first set it up. I'll just set the epochs to 10 for now. For epoch, in range epochs, let's well, do model.train. We named it model 0, right? 0.train. Then do the forward pass. What do we call the, we call it by logits. Yeah, so it's just here our output. Okay, by logits is gonna be just model 0, and we're gonna pass it the xtrain first, and then we're gonna calculate the loss. We're gonna do by logits, and we're gonna compare match.
Welcome back. In the last few videos, we've been working through creating a model for a classification problem, and now we're up to training a model. And we've got some steps here, but we started off by discussing the concept of logits. Logits are the raw output of the model, whatever comes out of the forward functions of the layers in our model. And then we discussed how we can turn those logits into prediction probabilities using an activation function, such as sigmoid for binary classification and softmax for multi-class classification. We haven't seen softmax yet, but we're going to stick with sigmoid for now because we have binary classification data. And then we can convert that from prediction probabilities to prediction labels. Because remember, when we want to evaluate our model, we want to compare apples to apples. We want our model's predictions to be in the same format as our test labels. And so I took a little break after the previous video. So my Colab notebook has once again disconnected. So I'm just going to run all of the cells before here. It's going to reconnect up here. We should still have a GPU present. That's a good thing about Google Colab, is that if you change the runtime type to GPU, it'll save that wherever it saves the Google Colab notebook, so that when you restart it, it should still have a GPU present. And how can we check that, of course? Well, we can type in device, we can run that cell, and we can also check NVIDIA SMI. It'll tell us if we have an NVIDIA GPU with CUDA enabled ready to go. So what's our device? CUDA, wonderful. And NVIDIA SMI, excellent. I have a Tesla P100 GPU ready to go. So with that being said, let's start to write a training loop. Now we've done this before, and we've got the steps up here. Do the forward pass, calculate the loss. We've spent enough on this, so we're just going to start jumping into write code. There is a little tidbit in this one though, but we'll conquer that when we get to it. So I'm going to set a manual seed, torch.manual seed, and I'm going to use my favorite number 42. This is just to ensure reproducibility if possible. Now I also want you to be aware of, there is also another form of random seed, manual seed, which is a CUDA random seed. Do we have the Pytorch? Yeah, reproducibility. So torch.cuda.manualseed.seed. There is a CUDA seed somewhere. Let's try and find out. CUDA. I think Pytorch have just had an upgrade to their documentation. Seed. Yeah, there we go. Okay, I knew it was there. So torch.cuda.manual seed. So if we're using CUDA, we have a CUDA manual seed as well. So let's see what happens if we put that, torch.cuda.manual seed. 42. We don't necessarily have to put these. It's just to try and get as reproducible as numbers as possible on your screen and my screen. Again, what is more important is not necessarily the numbers exactly being the same lining up between our screens. It's more so the direction of which way they're going. So let's set the number of epochs. We're going to train for 100 epochs. Epochs equals 100. But again, as you might have guessed, the CUDA manual seed is for if you're doing operations on a CUDA device, which in our case we are, well, then perhaps we want them to be as reproducible as possible. So speaking of CUDA devices, let's put the data to the target device because we're working with, or we're writing data agnostic code here. So I'm going to write xtrain, ytrain equals xtrain2device, comma, ytrain.toDevice. That'll take care of the training data. And I'm going to do this.
Okay, this is for to set up device agnostic code.
The same for the testing data equals xtest2device, because if we're going to run our model on the CUDA device, we want our data to be there too, and the way we're writing our code is going to be device agnostic. Have I said that enough yet? So let's also build our training and evaluation loop. Because we've covered the steps in here before, we're going to start working a little bit faster through here, and don't worry, I think you're up to it. So for an epoch and a range of epochs, what do? We start with training. So let me just write this. Training, model0.train, that's the model we're working with. We call the train, which is the default, but we're going to do that anyway. And as you might have guessed, the code that we're writing here is you can functionize this. So we're going to do this later on, but just for now, the next couple of videos, the next module or two, we're going to keep writing out the training loop in full. So this is the part, the forward pass, where there's a little bit of a tidbit here compared to what we've done previously. And that is because we're outputting raw logits here if we just pass our data straight to the model. So model 0 xtrain, and we're going to squeeze them here to get rid of an extra dimension. You can try to see what the output sizes look like without squeeze, but we're just going to call squeeze here. Remember, squeeze removes an extra 1 dimension from a tensor. And then to convert it into prediction.
Yeah, it removes an extra 1 dimension. Yep, agreed. Although, go up. Where we defined, yeah. Oh, is it because we have 2 layers that somehow there's an extra dimension?
Labels, we go torch.round and torch.sigmoid, because torch.sigmoid is an activation function, which is going to convert logits into what? Convert the logits into prediction probabilities. So y logits, and I'm just going to put a note here. So this is going to go turn logits into...
This is why I just pause for a bit, because we don't pass logits, right? We pass the predictions. Like, to calculate the loss, we need to compare apples to apples. Well, apples to almost apples, rather. That's the correct way of putting it. Yeah. So the y predictions are gonna be, so we have our logits, so we do torch.sigmoid, then we pass it our logits. What we're doing here is we're turning logits into prediction probabilities, which is this which is taken care of by the activation layer, that is sigmoid in this case, and then we convert that into predictions. Okay, alright, now let's compare this y pred into our predictions with our
pred probs into pred labels. So we've done the forward pass. So that's a little tidbit there. We could have done...
That's the loss for you, and then calculate the loss, and then yeah, optimize it. Wow, I'm seeing this out to you now. It's like memorized, like hardcore into my brain now. Alright, so we remove our gradient, or just reset the gradient so that we don't accumulate gradients later on when we do our step. Then we do the backward loss. And then we just do the step. Then we can do our training part too. Let's just
done all of this in one step, but I'll show you why we broke this apart. So now we're going to calculate loss/accuracy. We don't necessarily have to calculate the accuracy, but we did make an accuracy function up here so that we can calculate the accuracy during training. We could just stick with only calculating the loss, but sometimes it's cool to visualize different metrics, loss plus a few others, while your model is training. So let's write some code to do that here. So we'll start off by going loss equals loss fn and y logits. Here's the difference of what we've done before. Previously, in the notebook 01, we're up to 02 now, we passed in the prediction right here. But because, what's our loss function? Let's have a look at our loss function. Let's just call that, see what it returns. BCE with logits loss. So the BCE...
that's a tricky one. I see.
BCE with logits expects logits as input. So, as you might have guessed, loss function without logits, if we had nn.bce loss, notice how we haven't got with logits, and then we called loss fn. Fn stands for function, by the way. Without logits, what do we get?
The sigmoid function automatically for us. And look at that, we have a second viewer right now. Whoever's watching, welcome to my stream.
So BCE loss. So this loss expects prediction probabilities as input. So let's write some code to differentiate between these two. As I said, we're going to be sticking with this one. Why is that? Because if we look up torch BCE with logits loss, the documentation states that it's more numerically stable. So this loss combines a sigmoid layer and the BCE loss into one single class and is more numerically stable. So let's come back here. We'll keep writing some code. And the accuracy is going to be accuracy fn. So our accuracy function, there's a little bit of a difference here, is y true equals y trained for the training data. So this will be the training accuracy. And then we have y pred equals y pred. So
this will apply the sigmoid function automatically for us and then compare it against y trained. So we are, in fact, at the end we are going to compare apples to something which is like apples, I guess. Yeah, I guess that's a way to put it. Now we also calculate accuracy with our function that we have built. Let's misspell that. Accuracy function. What's it? Y true and Y prediction. Okay. Y true is gonna be training data, and then we compare that against our predictions. So this is the ground layer truth. That's what Y true. I guess that's what Y true implies. Anyhow.
This is our own custom accuracy function that we wrote ourselves. This is a testament to the Pythonic nature of Pytorch as well. We've just got a pure Python function that we've slotted into our training loop, which is essentially what the loss function is behind the scenes. Now, let's write here, nn.bce with logits loss expects raw logits, so the raw output of our model, as input. Now, what if we were using BCE loss on its own here? Well, let's just write some code for that. So let's call loss function, and then we want to pass in y pred, or we can just go y, or torch sigmoid. So why would we pass in torch sigmoid on the logits here? Because remember, calling torch.sigmoid on our logits turns our logits into prediction probabilities. And then we would pass in y train here. So if this was BCE loss, this expects prediction probabilities as input. So does that make sense? That's the difference between with logits. So our loss function requires logits as input, whereas if we just did straight up BCE loss, we need to call torch.sigmoid on the logits because it expects prediction probabilities as input. Now, I'm going to comment that out because our loss function is BCE with logits loss. But just keep that in mind. If for some reason you stumble across some Pytorch code that's using BCE loss, not BCE with logits loss, and you find that torch.sigmoid is calling here, or you come across some errors because your inputs to your loss function are not what it expects. So with that being said, we can keep going with our other steps. So we're up to optimizer 0 grad. So optimizer.0 grad. Oh, this is step 3, by the way. And what's after this? Once we've 0 graded the optimizer, we do number 4, which is loss backward. We can go loss backward. And then we go, what's next? Optimizer step, step, step. So optimizer.step. And I'm singing the unofficial Pytorch optimization loop song there. This is backpropagation. Calculate the gradients with respect to all of the parameters in the model. And the optimizer step is update the parameters to reduce the gradients. So gradient descent, hence the descent. Now, if we want to do testing, well, we know what to do here now. We go model 0, what do?
Wait, let me write that out first and then we'll come back. So for testing, we have to turn on the eval mode, and then should we do next, you ask? We need to switch to inference mode. And let's calculate the loss again. But first, let's get our training predictions. So that's gonna be test spread. Well, let's do it step by step. Let's get the test logits first, which is just gonna be what our model would output. So that's we're gonna pass an x test. I'm gonna get rid of the additional dimension there. Then we're gonna do the conversion step, which is we're gonna get to the labels. Basically, we'll activate our test logits with the sigmoid function. Which will then be rounded off to give our labels or basically our predictions as such for binary classification. Then we'll calculate our loss. Although, do we need a test accuracy? I guess there's no harm in putting that too. The more stats, the better, I say. Anyhow, so to calculate the loss, well, let's name it test loss so that we don't confuse ourselves here. Now we pass in the test predictions, and then we pass y test to compare apples to something which is like apples, I guess. And then let's also calculate our test accuracy. We're just gonna use our accuracy function. Let's put this on another line just to make it more pretty, I say. Then, you know what, let me just zoom in. The text would be, yeah, there we go. So our test accuracy, for our test accuracy, we're gonna use our accuracy function. Our ground truth is gonna be, any guesses? It's going to be test prediction. It's not gonna be test predictions. What did I just say? It's of course gonna be our y test. And then our predictions are gonna be, of course, our test predictions that we just have. That should be good enough. Yep, and we'll print what's happening. Let's print the epoch count. You know what? We'll just copy what printing.
We call model.eval when we're testing. And if we're making predictions, that's what we do when we test. We make predictions on the test data set using the patterns that our model has learned on the training data set. We turn on inference mode because we're doing inference. We want to do the forward pass. And of course, we're going to compute the test logits because logits are the raw output of our model with no modifications. Xtest.squeeze. We're going to get rid of an extra one dimension there. Then we create the test pred, which is, we have to do a similar calculation to what we've done here for the test pred, which is torch.round. For our binary classification, we want prediction probabilities, which we're going to create by calling the sigmoid function on the test logits. Prediction probabilities that are 0.5 or above to go to 1, and prediction probabilities under 0.5 to go to label 0. So 2 is calculate the test loss / accuracy. How would we do this? Well, just as we've done before. And we're going to go loss fn, test logits, because our loss function, we're using what? We're using BCE with logits loss, expects logits as input. Where would we find that out? In the documentation, of course. Then we come back here, test logits. We're going to compare that to the y test labels. And then for the test accuracy, what are we going to do? We're going to call accuracy fn on y true equals y test and y pred equals test pred. Now you might be thinking, why did I switch up the order here for these? Oh, and by the way, this is important to know with logits loss. So with these loss functions, the order here matters of which way you put in your parameters. So predictions come first and then true labels for our loss function. You might be wondering why I've done it the reverse for our accuracy function, y true and y pred. That's just because I like to be confusing. Well, not really. It's because if we go to scikit-learn, I base a lot of my structured code off how
That's a funny way to put it.
scikit-learn structures things. The scikit-learn metrics accuracy score goes y true, y pred. So I base it off of that order because the scikit-learn metrics package is very helpful. So I've based our metric evaluation metric function off this one. Whereas Pytorch's loss function does it in the reverse order, and it's important to get these in the right order. Exactly why they do it in that order, I couldn't tell you why. And we've got one final step, which is to
Someone in the developer who was creating the model just decided to, and now we're stuck with that.
print out what's happening. So how about we go, we're doing a lot of epochs here, 100 epochs. So we'll divide the epoch by 10 to print out every epoch, or every 10th epoch, sorry.
Every 10th.
And we have a couple of different metrics that we can print out this time. So we're going to print out the epoch number, epoch, and then we're going to print out the loss. So loss, how many decimal points? We'll go 0.5
Yeah, there we go.
here. This is going to be the training loss. We'll also do the accuracy, which will be the training accuracy. We could write train ac here for our variable to be a little bit, make them a little bit more understandable. And then we go here, but we're just going to leave it as loss and accuracy for now because we've got test loss over here. Test loss. And we're going to do the same, 5 decimal points here. And then we're going to go test accuracy as well. Test ac dot. We'll go 2 for the accuracy. And because it's accuracy, we want a percentage. So this is the percent out of 100 guesses. What's the percentage that our model gets right on the training data and the testing data? As long as we've coded all the functions. Correct. So this is the percent out of test ac dot name. Leave it as d. With how many decimal points? We'll go 0.5 here. This is
Oh, that's a way to do it. We have strings. I've seen it in a short, but this is my first time actually using it.
going to be the training loss. We'll also do the accuracy, which will be the training accuracy. We could write train ac here for our variable to be a little bit, make them a little bit more understandable. And then we go here, but we're just going to leave it as loss and accuracy for now because we've got test loss over here. Test loss. And we're going to do the same. Same 5 decimal points here. And then we're going to go test accuracy as well. Test ac dot. We'll go 2 for the accuracy. And because it's accuracy, we want a percentage. This is the percent out of 100 guesses. What's the percentage that our model gets right on the
Let's put the person sign here too.
training data and the testing data, as long as we've coded all the functions correctly. Now, we've got a fair few steps.
This should be good enough, although why am I saying oh, because I did not. Maybe if I see. With that extra bracket there. That should fix it, right? Yep, looks good enough for me.
Here. My challenge to you is to run this, and if there are any errors, try to fix them. No doubt there's probably one or two or maybe more that we're going to...
Alright, okay, let's take up that challenge. Let's zoom out too. No, other than the others, let's see here. What's happening here? No, it is getting better.
going to have to fix in the next video. But speaking of next videos, I'll see you there. Let's train our first.
Accuracy is increasing, although a bit weird on the for our test accuracy. It increased and decreased, and it's all
Classification model. Oh, this is very exciting. I'll see you soon. Welcome back. In the last video, we wrote a mammoth amount of code, but nothing that we can't handle. We've been through a lot of these steps. We did have to talk about a few tidbits between using different loss functions, namely the BCE loss, which is binary cross entropy loss, and the BCE with logits loss. We discussed that the BCE loss in Pytorch expects prediction probabilities as input, so we have to convert our model's logits. Logits are the raw output of the model to prediction probabilities using the torch.sigmoid activation function. And if we're using BCE with logits loss, it expects raw logits as input, as sort of the name hints at. And so we just pass it straight away, the raw logits. Whereas our own custom accuracy function compares labels to labels. And that's kind of what we've been stepping through over the last few videos, is going from logits to pred probs to pred labels, because that's the ideal output of our model, is some kind of label that we as humans can interpret. And so let's keep pushing forward. You may have already tried to run this training loop. I don't know if it works. We wrote all this code together in the last video, and there's probably an error somewhere. So you ready? We're going to train our first classification model together for 100 epochs. If it all goes to plan, in 3, 2, 1, let's run. Oh my gosh, it actually worked the first go. I promise you I didn't change anything in here from the last video. So let's inspect what's going on. It trains pretty fast. Why? Well, because we're using a GPU, so it's going to be accelerated as much as it can anyway. And our data set is quite small, and our network is quite small. So you won't always get networks training this fast. It did 100 epochs in like a second. So the loss, 0.69973. It doesn't go down very much. The accuracy even starts high and then goes down. What's going on here? Our model doesn't seem to be learning anything. So what would an ideal accuracy be? An ideal accuracy is 100. And what's an ideal loss value? Well, 0, because lower is better for loss. This is confusing. And now if we go have a look at our blue and red dots, where's our data? So I reckon, do we still have a data frame here? How many samples do we have of each? Let's inspect. Let's do some data analysis. Where do we create a data frame? Here. Now, circles. Do we still have this instantiated? Circles.label. We're going to call on pandas here. Value counts. Is this going to output how many of each? Okay. Wow. We've got 500 of class 1 and 500 of class 0. So we have 500 red dots and blue dots, which means we have a balanced data set. So if we're basically trying to predict heads or tails here. So if we're getting an accuracy of under 50% or about 50% if you rounded it up, our model is basically doing as
That's random, right?
well as guessing. Well, what gives? Well, I think we should get visual with this. So let's make some predictions with our model, because these are just numbers on the page. It's hard to interpret what's going on, but our intuition now is because we have 500 samples of each, or in the case of the training data set, we have 400 of each because we have 800 samples in the training data set, and we have in the testing data set, we have 200 total samples, so we have 100 of each. We're basically doing a coin flip here. Our model is as good as guessing. So, time to investigate why our model is not learning. And one of the ways we can do that is by visualizing our predictions. So let's write down here from the metrics. It looks like our model isn't learning anything. So to inspect it, let's make some predictions and make them visual. And we'll write down here, in other words, visualize, visualize, visualize. All right. So we've trained a model. We've at least got the structure for the training code here. Like, this is the right training code. We've written this code before. So we know that this setup for training code does allow a model to train. So there must be something wrong with either how we've built our model, the data set, but let's get going and investigate together. So to do so, I've got a function that I've pre-built earlier. Did I mention that we're learning side by side of a machine learning cooking show? So this is an ingredient I prepared earlier, a part of the dish. So to do so, we're going to import a function called plot decision, or maybe I'll turn this into code, plot decision boundary. Welcome to the cooking show, cooking with machine learning. What model will we cook up today? So if we go to Pytorch deep learning, well, it's already over here, but this is the home repo for the course. The link for this will be scattered everywhere. But there's a little function here called helperfunctions.py, which I'm going to fill up with helper functions throughout the course. And this is the one I'm talking about here. Plot decision boundary. Now, we could just copy this into our notebook, or I'm going to write some code to import this programmatically so we can use other functions from in here. Here's our plot predictions function that we made in the last section, 01. But this plot decision boundary is a function that I got inspired by to create from madewithml.com. Now, this is another resource, a little bit of an aside. I highly recommend going through this by Goku Mohandas. It gives you the foundations of neural networks and also ML ops, which is a field which is based on getting your neural networks and machine learning models into applications that other people can use. So I can't recommend this resource enough. So please, please, please check that out if you want another resource for machine learning. But this is where this helper function came from. So thank you, Goku Mohandas. I've made a little bit of modifications for this course, but not too many. So we could either copy that, paste it in here, or we could write some code to import it for us magically, or using the power of the internet, right? Because that's what we are. We're programmers, we're machine learning engineers, we're data scientists. So from pathlib, so the request module in Python is a module that allows you to make requests. A request is like going to a website, hey, I'd like to get this code from you, or this information from you, can you please send it to me? So that's what that allows us to do. And pathlib, we've seen pathlib before, but it allows us to create file paths. Because why? Well, we want to save this helperfunction.py script to our Google Colab files. And so we can do this with a little bit of code. So download helper functions from learn Pytorch repo if it's not already downloaded. So let's see how we can do that. So we're going to write some if-else code to check to see if the path of helperfunctions.py already exists. We don't want to download it again. So at the moment it doesn't exist, so this if statement is going to return false. So let's just print out what it does if it returns true. Helperfunctions.py already exists. We could even probably do a try and except loop here, but if else will help us out for now. So if it exists, else, print, downloading, helperfunctions.py. So ours doesn't exist, so it's going to make a request, or let's set up our request, requests.get, and here's where we can put in a URL, but we need the raw version of it. So this is the raw version. If we go back, this is just Pytorch Deep Learning, the repo for this course, /helperfunctions. If I click raw, I'm going to copy that. Oh, don't want to go in there. I want to go into request get, type that in. This has to be in a string format. So we get the raw URL, and then we're going to go with open. We're going to open a file called helperfunctions.py, and we're going to set the context to be write binary, which is WB, as file. F is a common short version of writing file, because we're going to call file.write, and then request.content. So this code is basically saying, hey, request, get the information that's at this link here, which is, of course, all of this code here, which is a Python script. And then we're going to create a file called helperfunctions.py, which gives us write permissions. We're going to name it F, which is short for file. And then we're going to call on it file.write the content of the request. So instead of talking through it, how about we see it in action? We'll know if it works if we can, from helper functions, import plot predictions. We're going to use plot predictions later on, as well as plot decision boundary. So plot predictions we wrote in the last section. Wonderful. I'm going to write here, downloading helperfunctions.py. Did it work? We have helperfunctions.py. Look at that. We've done it programmatically. Can we view this in Google Colab? Oh.
I like how Daniel is excited for every single thing. He is the most optimistic tutor I've ever seen. But first let's run this and download it. Now where would I get the link? Is it under the description of the course by chance? Go GitHub. Alright, so we have to go to the GitHub page and then copy the URL. So where exactly would that be? GitHub has a search function, search bar though. If I could find it, or go to file, maybe it's that, yeah, there we go. Help functions.py. Let's copy this, and let's put that URL here. That should work, although what's happening here? Oh, it's not request, we named it. We named the variable as SAR. If I run this, and if I view files, very good. So let's just full screen this for a bit. Although this is not .py, this is HTML. What exactly did he copy? Let's see. So bad go. Are there any discussions here? People are still going through this. Look at this for as I go in general typo. That's cool. Anyhow, go to file, help functions, apply, and what exactly is the link that he has? Or raw.github user content. Let me guess. Raw.github user content. That should work, right?
Sorry, but we're because we're going to the raw version of it. So this is the request.get, and here's where we can put in a URL, but we need the raw version of it. So
okay, raw version of it. There we go. Let's copy that then. Let's delete this. Yep, because that's HTML, not what we want. And let's close this, replace this URL, and that should work. Yep, let's open up helperfunctions.py. There we go, that looks way better, isn't it? Alright, cool. Let's run.
So this is the raw version. If we go back, this is just Pytorch Deep Learning, the repo for this course, /helper functions. If I click raw, I'm going to copy that. Oh, don't want to go in there. I want to go into request get, type that in. This has to be in a string format. So we get the raw URL, and then we're going to go with open. We're going to open a file called helperfunctions.py, and we're going to set the context to be right. Helper functions import plot predictions. We're going to use plot predictions later on, as well as plot decision boundary. So plot predictions we wrote in the last section. Wonderful. I'm going to write here, downloading helperfunctions.py. Did it work? We have helperfunctions.py. Look at that. We've done it programmatically. Can we view this in Google Colab? Oh my goodness, yes we can. Look at that. So this may evolve by the time you do the course, but these are just some general helper functions rather than writing all of this out. If you would like to know what's going on in plot decision boundary, I encourage you to read through here and what's going on. You can step by step it yourself. There is nothing here that you can't tackle yourself. It's all just Python code. No secrets, just Python code. We're making predictions with a Pytorch model, and then we're testing for multi-class or binary. So we're going to get out of that. But now let's see.
That correctly.
The ultimate test is if the plot decision boundary function works. So again, we could discuss plot decision boundary of the model. We could discuss what it does behind the scenes till the cows come home. But we're going to see it in real life here. I like to get visual. So fig size 12.6, we're going to create a plot here because we are adhering to the Data Explorer's motto of visualize, visualize, visualize. And we want a subplot because we're going to compare our training and test sets here. Train, and then we're going to go PLT, or actually, we'll plot the first one, plot decision boundary. Now, because we're doing a training plot here, we're going to pass in model 0 and xtrain and ytrain. Now, this is the order that the parameters go in. If we press Command-Shift-Space, I believe Google Colab, if it's working with me, will put up a doc string. There we go, plot decision boundary. Look at the inputs that it takes. Model, which is torch nn.module. And we've got x, which is our x value, which is the torch tensor, and y, which is our torch tensor value here. So that's for the training data. Now, let's do the same for the testing data. Plot.
Just writing the code that he's writing right now, since this isn't, directly related to machine learning as such. But it does mean that we need to go back and look a bit more in depth into the other libraries which almost always come along with machine learning, like matplotlib, numpy, and so on. Even pandas. Although it is safe to say I have some experience with pandas and numpy, but not with matplotlib though.
Subplot. This is going to be 1, 2, 2 for the index. This is just number of rows of the plot, number of columns, and this is the index. So this plot will appear on the first slot. We're going to see this anyway. Anything below this code will appear on the second slot. plt.title, and we're going to call this one test. Then we're going to call plot decision boundary. If this works, this is going to be some serious magic. I love visualization functions in machine learning. Okay, you ready? 3, 2, 1. Let's check it out. How's our model doing? in functions in machine learning. Okay, you ready? 3.
No, it's not because this is test, right? So it's test, and by test is what we should pass as arguments, and that's taking some time. Anyhow, there we go. Right, what do we have?
3, 2, 1. Let's check it out. How's our model doing?
Oh, is it like
Look at that.
Right.
Oh, now it's clear. So behind the scenes, this is the plots that plot decision boundary is making. Of course, this is the training data. This is the testing data. Not as many dot points here, but the same sort of line of what's going on. So this is the line that our model is trying to draw through the data. No wonder it's getting about 50% accuracy and the loss isn't going down. It's just trying to split the data straight through the middle. It's drawing a straight line, but our data is circular. Why do you think it's drawing a straight line? Well, do you think it has anything to do with the fact that our model is just made using pure linear layers? Let's go back to our model. What's it comprised of? Just a couple of linear layers. What's a linear line? If we look up linear line, is this going to work with me? I don't actually think. It might. There we go. Linear line. All straight lines. So I want you to have a think about this. Even if you're completely new to deep learning, you can answer this question. Can we ever separate this circular data with straight lines? I mean, maybe we could if we drew straight lines here, but then trying to curve them around. But there's an easier way. We're going to see that later on. For now,
if we draw, I mean, in a way, aren't circles just tiny lines made up together then? Mind blown.
how about we try to improve our model? So the model that we built, we've got 100 epochs. I wonder if our model will improve if we trained it for longer. So that's a little bit of a challenge before the next video. See if you can train the model for 1,000 epochs. Does that improve the results here? And if it doesn't improve the results here, have a think about why that might be. I'll see you in the next video. Welcome back. In the last video, we wrote some code to download a series of helper functions from our helperfunctions.py. And later on, you'll see why this is quite standard practice as you write more and more code, is to write some code, store them somewhere, such as a Python script like this. And then instead of us rewriting everything that we have in helper functions, we just import them and then use them later on. This is similar to what we've been doing with Pytorch. Pytorch is essentially just a collection of Python scripts that we're using to build neural networks. Well, there's a lot more than what we've just done. I mean, we've got one here, but Pytorch is a collection of probably hundreds of different Python scripts. But that's beside the point. We're trying to train a model here to separate blue and red dots. But our current model is only drawing straight lines. And I got you to have a think about whether our straight line model, our linear model, could ever separate this data. Maybe it could. And I issued the challenge to see if it could if you trained for 1,000 epochs. So did it improve at anything? Is the accuracy any higher? Well, speaking of training for more epochs, we're up to section number 5, improving a model. This is from a model perspective. So now let's discuss some ways if you were getting results after you train a machine learning model or a deep learning model, whatever kind of model you're working with, and you weren't happy with those results. So how could you go about improving them? So this is going to be a little bit of an overview of what we're going to get into. So one way is to add more layers. So give the model more chances to learn about patterns in the data. Why would that help? Because if our model currently has 2 layers, model 0.stateDict, well, we've got however many numbers here, 20 or so. So this is 0th layer, this is the first layer. If we had 10 of these, well, we'd have 10 times the amount of parameters to try and learn the patterns in this data, a representation of this data. Well, we've got however many numbers here, 20 or so. So this is 0th layer, this is the first layer. If we had 10 of these, well, we'd have 10 times the amount of parameters to try and learn the patterns in this data, a representation of this data. Another way is to add more hidden units. So what I mean by that is we created this model here, and each of these layers has 5 hidden units. The first one outputs, out features equals 5, and this one takes in features equals 5. So we could go from 5 hidden units to 10 hidden units. The same principle as above applies here, is that the more parameters our model has to represent our data, that potentially, now I say potentially here because some of these things might not necessarily work. So our data set's quite simple. So maybe if we added too many layers, our model's trying to learn things that are too complex. It's trying to adjust too many numbers for the data set that we have. The same thing for more hidden units. What other options do we have? Well, we could fit for longer, give the model more of a chance to learn because every epoch is one pass through the data. So maybe 100 times looking at this data set wasn't enough. So maybe you could fit for 1,000 times, which was the challenge. Then there's changing the activation functions, which we're using sigmoid at the moment, which is generally the activation function you use for a binary classification problem. But there are also activation functions you can put within your model. There's a little hint. We'll get to that later. Then there's change the learning rate. So the learning rate is the amount the optimizer will adjust these every epoch. And if it's too small, our model might not learn anything because it's taking forever to change these numbers. But if also on the other side of things, if the learning rate is too high, these updates might be too large and our model might just explode. There's an actual problem in machine learning called exploding gradient problem, where the numbers just get too large. On the other side, there's also a vanishing gradient problem, where the gradients just go basically to 0 too quickly. And then there's also change the loss function. But I feel like for now, sigmoid and binary cross entropy are pretty good, pretty standard. So we're going to have a look at some options here, add more layers and fit for longer, maybe changing the learning rate. But let's just add a little bit of color to what we've been talking about. Right now, we've fit the model to the data and made a prediction. I'm just going to step through this. Where are we up to? We've done this, we've done this, we've done these two, we've built a training loop, we've fit the model to the data, made a prediction, we've evaluated our model visually, and we're not happy with that. So we're up to number 5. We're going to improve through experimentation. We don't need to use TensorBoard just yet. We're going to talk about this at a high level. TensorBoard is a tool or a utility from Pytorch, which helps you to monitor experiments. We'll see that later on. And then we'll get to this. We won't save our model until we've got one that we're happy with. And so, if we look at what we've just talked about, improving a model from a model's perspective, let's talk about the things we've talked about with some color this time. So, say we've got a model here. This isn't the exact model that we're working with, but it's similar structure. We've got 1, 2, 3, 4 layers. We've got a loss function, BCE, with logits loss. We've got an optimizer, stochastic gradient descent. And if we did write some training code, this is 10 epochs. And then the testing code here, I've just cut it out because it wouldn't fit on the slide. Then if we wanted to go to a larger model, let's add some color here so we can highlight what's happening. Adding layers. Okay, so this one's got 1, 2, 3, 4, 5, 6 layers. And we've got another color here, which is, I'd say this is like a little bit of a greeny blue. Increase the number of hidden units. Okay, so the hidden units are
That's technically that's aqua, right?
these features here. We've gone from 100 to 128 to 128. Remember, the out features of a previous layer have to line up with the in features of a next layer. And then we've gone to 256. Wow. So remember how I said multiples of 8 are pretty good generally in deep learning? Well, this is where these numbers come from. And then what else do we have? Change/add activation functions. We haven't seen this before, nn.relu. If you want to jump ahead and have a look at what nn.relu is, how would you find out about it? Well, I just Google nn.relu. But we're going to have a look at what this is later on. We can see here that this one's got 1, but this larger model has some relus scattered between the linear layers. Maybe that's a hint. If we combine a linear layer with a relu, what's a relu layer? I'm not going to spoil this. We're going to find out later on. Change the optimization function. Oh, okay, so we've got SGD. Do you recall how I said Atom is another popular one that works fairly well across a lot of problems as well? So Atom might be a better option for us here. The learning rate as well. So maybe this learning rate was a little too high, and so we've divided it by 10. And then finally, fitting for longer. So instead of 10 epochs, we've gone to 100. So how about we try to implement some of these with our own model to see if it improves what we've got going on here? Because frankly, like, this isn't satisfactory. We're trying to build a neural network here. Neural networks are supposed to be these models that can learn almost anything, and we can't even separate some blue dots from some red dots. So in the next video, how about we run through writing some code to do some of these steps here? In fact, if you want to try yourself, I'd highly encourage that. So I'd start with trying to add some more layers and add some more hidden units and fitting for longer. You can keep all of the other settings the same for now. But I'll see you in the next video. Welcome back. In the last video, we discussed some options to improve our model from a model perspective. And namely, we're trying to improve it so that the predictions are better, so that the patterns it learns better represent the data, so we can separate blue dots from red dots. And you might be wondering why we said from a model perspective here. So let me just write these down. These options are all from a model's perspective because they deal directly with the model rather than the data. So there's another way to improve a model's results is if the model was sound already. In machine learning and deep learning, you may be aware that generally if you have more data samples, the model learns or gets better results because it has more opportunity to learn. There's a few other ways to improve a model from a data perspective, but we're going to focus on improving a model from a model's perspective. So, and because these options are all values we as machine learning engineers and data scientists.
What did I just do there? Let's try and fix that now. I touched my lens and somehow. Let me just troubleshoot that. For the camera, it sure does indeed fire up quite a lot. Let's how do we fix this? Oh, we have a third viewer now. Hey there, who was watching. I'm just trying to fix my camera here. Da-da-da. That should hopefully fix that, I hope at least. And yeah, you see the camera icon. Okay, alright, there we go. Okay, I do need to look into my camera getting really hot here. I use my phone's camera, so maybe buy a webcam or something. Anyhow, thank you for joining my stream. You know, put any questions you have, feel free to ask them in chat. For now, it's me just
Can change. They are referred to
tutorial.
as hyperparameters. So a little bit of an important distinction here. Parameters are the numbers within a model. The parameters here, like these values, the weights and biases, are parameters, are the values a model updates by itself. Hyperparameters are what we as machine learning engineers and data scientists, such as adding more layers, more hidden units, fitting for longer, number of epochs, activation functions, learning rate, loss functions, are hyperparameters because they're values that we can change. So let's change some of the hyperparameters of our model. So we'll create circle model v1. We're going to import from nn.module as well. We could write this model using nn.sequential, but we're going to subclass nn.module for practice. Why would we use nn.sequential? Well, because as you'll see, our model is not too complicated, but we subclass nn.module. In fact, nn.sequential, so if we write here, nn.sequential, is also a version of nn.module. But we subclass nn.module here for practice, and for later on, if we wanted to, or if you wanted to make more complex models, you're going to see a subclass of nn.module a lot in the wild. So the first change we're going to update is the number of hidden units. So out features, I might write this down before we do it. Let's try and improve our model by adding more hidden units. So this will go from 5 and we'll increase it to 10. And we want to increase the number of layers. So we want to go from 2 to 3. We'll add an extra layer and then increase the number of epochs. So we're going to go from 100 to 1,000. Now, we're going to put on our scientist hats for a second. What would be the problem with the way we're running this experiment? If we're doing all 3 things in one hit, why might that be problematic? Well, because
we wouldn't know which parameters affecting what.
Might not know which one offered the improvement, if there is any improvement, or degradation. So, just to keep in mind going forward, I'm just doing this as an example of how we can change all of these. But generally, when you're doing machine learning experiments, you'd only like to change one value at a time and track the results. So that's called experiment tracking in machine learning. We're going to have a look at experiment tracking a little later on in the course, but just keep that in mind. A scientist likes to change one variable of what's going on so that they can control what's happening. But we're going to create this next layer here, layer 2, and of course it takes the same number of out features as in features as the previous layer. This is 2 because why? Our X train has, let's look at just the first 5 samples, has 2 features. So now we're going to create self layer 3, which equals nn.linear. The in features here is going to be 10. Why? Because the layer above has out features equals 10. So what we've changed here so far is we've got hidden units previously in V0 of this model was 5, and now we've got a third layer, which previously before was 2. So these are 2 of our main changes here, and out features equals 1 because why? Let's have a look at, speaking of why, our y
Oops, that's too many capital letters. So we have 3 layers this time. That's okay, I guess.
is just one number. So remember, the shapes, the input and output shapes of a model is one of the most important things in deep learning. We're going to see different values for these shapes later on, but because we're working with this data set, we're focused on 2 in features and 1 out feature. So now that we've got our layers prepared, what's next? Well, we have to override the forward method because every subclass of nn.module has to implement a forward method. So what are we going to do here? Well, let me just show you one option. We could go Z, which would be Z for logits. Logits is actually represented by Z, fun fact, but you could actually put any variable here. So this could be X1, or you could reset X if you wanted to. I just like putting a different one because it's a little less confusing for me. And then we could go update Z by going self layer 2, and then because Z above is the output of layer 1, it now goes into here. And then if we go Z, again, equals self layer 3, what's this going to take? It's going to take Z from above. So this is saying, hey, give me X, put it through layer 1, assign it to Z, and then create a new variable Z, or override Z with self layer 2 with Z from before as the input. And then we've got Z again, the output of layer 2 as the input of layer 3. And then we could return Z. So that's just passing our data through each one of these layers here. But a way that you can leverage speedups in Pytorch is to call them all at once. So layer 3, and we're going to put self dot layer 2. And this is generally how I'm going to write them. But it also, behind the scenes, because it's performing all the operations at once, you leverage whatever speedups you can get. Oh, this should be layer 1. So it goes in order here. So what's happening? Well, it's computing the inside of the brackets first. So layer 1, X is going through layer 1. And then the output of X into layer 1 is going into layer 2. And then the same again for layer 3. So this way of writing operations leverages speedups where possible behind the scenes. And so we've done our forward method there. We're just passing our data through layers with extra hidden units and an extra layer overall. So now let's create an instance of circle model v1, which we're going to set to model 1. And we're going to write circle model v1, and we're going to send it to the target device because we like writing device agnostic code. And then we're going to check out model 1. So let's have a look at what's going on there. Beautiful. So now we have a 3-layered model with more hidden units. So I wonder if we trained this model for longer, are we going to get improvements here? So my challenge to you is we've already done these steps before. We're going to do them over the next couple of videos for completeness. But we need to what? Create a loss function. So I'll give you a hint. It's very similar to the one we've already used. And we need to create an optimizer. And then once we've done that, we need to write a training and evaluation loop for model 1. So give that a shot. Otherwise, I'll see you in the next video.
Wait, create a loss function, create an optimizer, write a training and evaluation loop for model 1. Alright, let's get to coding. Let's run that. So our loss function is just gonna be well, we have to import two things, right? So loss function is, we are going to keep that to BCA with logit loss and binary process entropy, right? That's what BC stands for. And optimizer would be stochastic gradient descent. So from torch dot loss import, maybe it's not torch dot loss, torch loss, or it's from torch dot neural network dot loss, I believe that. BC. Okay, then just from torch dot loss. Yeah. Then from torch dot optim, which is short for optimizers, I believe, import sgt. Alright, now what we're gonna do is we're gonna assign that here BCE with logit loss is gonna be our loss function. Do we need to call the function though? I keep forgetting. BCE, yeah, we need to call the function. And our optimizer is gonna be sgd, and for that we're gonna pass in our model one dot to spell it correctly, parameters, and the learning rate is gonna be, let's put that to 0.01. Okay, so we have created the loss function and optimizer. Now time to create our training loop. So let's do that. So what we're gonna do is, first and foremost, we need to create device agnostic code. So after we set the epochs, let's send our xtrain, ytrain, then our xtest and ytest to our device. Do we have double cursor? There you go. Can put multiple cursors on Google Colab apparently, which is pretty helpful. Just gonna do we're just gonna transfer that to our device, and that should do it. Although this should be capital, right? Font with that. Right. Now for let's do our loop for epoch and epochs. I mean range of epochs rather. What we're gonna do is we're gonna first of all switch our model to training mode, and then calculate the forward, do the forward pass, and calculate what am I saying, do the forward pass, which will result in our logits, which we would be representing by, let's just do by logits, by logits. Now what we're gonna do is we're gonna convert it into labels. Now how do we do that exactly? We pass in or rather we activate we use our activation layer, which we have decided as sigmoid, and we pass in the logits into that. So we've got our predictions now. Next what we want to do is calculate the loss. So let's try that, calculating, well, let's calculate both loss and accuracy. For that what we're going to do is by loss, loss is going to be our loss function, and are we going to pass in y predictions or logits? We're going to pass in logits. Why? Because PC with logits would activate it before comparing it. And then what do we need to compare it against? We need to compare it against our y train. Okay, cool. Now let's also calculate our meta type for that, didn't I? Let's calculate, we have our loss, let's calculate our accuracy. This is gonna be, we're gonna call our accuracy function, and then our ground truth is gonna be our y train, and our y predictions are just gonna be our y predictions. Let's change this variable name though. Anyhow, so we have our loss and accuracy. Now we're gonna set our optimizer to 0 grad, so that our gradients will accumulate, and then we have to calculate our loss backwards, not backward, and we're gonna step our optimizer. Let's also do our evaluation loop right now. So we're gonna do well, first let's switch to eval mode, then bit open torch dot inference mod. Well, not with open, we don't need to open anything. That should do. We're gonna calculate our test loss. Well, first let's get our I think this time we can just do test predictions immediately, right? Because we wouldn't need the, oh, you know, when we need the logic. So test logics is gonna be model 1 x tests, then our, we're getting really good at this, huh? Then our test predictions or test labels are gonna be, we're gonna activate our, well, use our activation function on our test predictions, or test logics rather, not our test predictions. Okay, then what are we gonna do? We're finally gonna calculate our test loss, for which we'll pass in our test logics, and then we'll also pass in our y test, because that's what we have to compare it against. Let's also have our test accuracy, which is gonna be our accuracy function. I'm just gonna copy this to speed things up, and our y true is gonna be y test, and our y pred is gonna be our test predictions. So we have our test accuracy now, and if our epoch count is like for we'll only do print what's happening for every 10th epoch.
We'll do this all together.
Against the code that
Welcome back. In the last video, we subclassed nm.module to create circle model v1, which is an upgrade on circle model v0 in the fact that we added more hidden units, so from 5 to 10, and we added a whole extra layer, and we've got an instance of it ready to go. So we're up to, in the workflow, we've got our data. Well, we haven't changed the data, so we've built our new model. We now need to pick a loss function, and I hinted at before that we're going to use the same loss function as before, the same optimizer. You might have already done all of these steps, so you may know whether this model works on our data set or not, but that's what we're going to work towards finding out in this video. So we've built our new model. Now let's pick a loss function and optimizer. We could almost do all of this with our eyes closed now. Build a training loop, fit the model to the data, make a prediction, and evaluate the model. We'll come back here, and let's set up a loss function. And by the way, if you're wondering, like, why would adding more features here, we've kind of hinted at this before, and why would an extra layer improve our model? Well, again, it's back to the fact that if we add more neurons, if we add more hidden units, and if we add more layers, it just gives our model more numbers to adjust. So look at what's going on here. Layer 1, layer 2. Look how many more we have compared to model 0, .static. We have all of these. This is model 0, and we just upgraded it. Look how many more we have from just adding an extra layer and more hidden units. So now we have our optimizer can change these values to hopefully create a better representation of the data we're trying to fit. So we just have more opportunity to learn patterns in our target data set. So that's the theory behind it. So let's get rid of these. Let's create a loss function what are we going to use? Well, we're going to use nn.bce with logits loss. And our optimizer is going to be what? We're going to keep that as the same as before, torch.optim.sgd. But we have to be aware that because we're using a new model, we have to pass in params of model 1. These are the parameters we want to optimize, and the LR is going to be 0.1. Is that the same LR we used before, learning rate 0.1? Oh, potentially our learning rate may be too big, 0.1. Where do we create our optimizer? So we've written a lot of code here. Optimizer, there we go, 0.1, that's right. So we'll keep it at 0.1 just to keep as many things the same as possible. So we're going to set up torch.manualseed 42 to make training as reproducible as possible, torch.cuda.manualseed 42. Now, as I said before, don't worry too much if your numbers aren't exactly the same as mine. The direction is more important, whether it's good or bad direction. So now let's set up epochs. We want to train for longer this time as well. So 1,000 epochs. This is one of our 3 improvements that we're trying to do. Adding more hidden units, increase the number of layers, and increase the number of epochs. So we're going to give our model 1,000 looks at the data to try and improve its patterns. So put data on the target device. We want to write device agnostic code. And yes, we've already done this, but we're going to write it out again. Practice what's going on. And the testing in array. And what's so model 1, we're going to pass it that.squeeze void on our
Oh yeah, we had to remove the extra dimension, although that should not
logits to go from logits to prediction probabilities to prediction labels. And then what do we do next? Well, we calculate the loss / accuracy. Our loss function is going to take in, I wonder if it'll work with just straight up ypred. I don't think it will because we need logits in here. Why loading BCE with logits learning? Because why? Oh, Google collabs our accuracy now, which is our accuracy function. And ypred, might notice what we're doing, propagation, previous presentation, and because we're making X testing in the middle of the screen, then I'm going to put in test pred here. How do we get from logits to predictions? Well, binary classification problem, logits, accuracy, test pred. So the test print. So because we're epoch, because the test loss has test at the front of it, and then accuracy here. Now, of course, this is going to be test loss. Who much? Have we got any errors here? I don't know. We've just all coded this freehand, right? There's limits on each layer. Let's see what we've got. 3, 2, 1, run. Oh.
So I might have reassigned extrainer to something else, perhaps. I mean, we did not make a mistake on sending it to the correct device, did we? To device. Extrain by train.
Predict next test, and we're going to squeeze them because we don't.
You know what? We're just gonna go up and just reassign whatever extrain and y train supposed to be. We'll just run on. Or too much code here. It's a good thing. We ran everything. Alright, chat, seems like we have to troubleshoot this now. Okay, what does it say? Linear. Argument input must be tensor, not linear. Wait, if it came here, then our previous code needed to have run, right? Does this work? That still works, so maybe we can try copying this. But we haven't set our manual seed, but I'm pretty sure that shouldn't make it's just for reproducibility, right? And nope, not it. Maybe we made a mistake while defining the class then. Self.layer 3, self.layer. Oh, there we go. That's would be the reason. Made a mistake while defining the class. Okay, torch.tensor. Let's redefine that. And
I want the extra 1 dimension from logit to convert logit to calculation, and we're going and y pred equals test pred, so the test predictions here. And our final step is to print out what's happening. So print out what's happening. Oh, every tutorial needs a song. If I could, I'd teach everything with song and dance. So because we're training for 1,000 epochs, how about every 100 epochs we print out something? So print f string, and we're going to write epoch in here so we know what epoch our model's on.
torch.sigma, oh, it's not sigmod, it's sigmoid. We got a lot of typos apparently. What's the problem here? Test logits. The dimensions don't match because we need to squeeze whatever comes out of here, don't we? Why do I keep on making of typos all of a sudden? Okay, now what? There we go. Oh, don't be. It's the other way around, didn't I? What do we do here? Okay, is equal to 0. You know, let's just put equals to 0 and then just redefine our class. Boom, there we go.
And then we're going to print out the loss. Of course, this is going to be the training loss because the test loss has test at the front of it. And then the accuracy here. Now, of course, this is going to be the training accuracy. We go here. And then we're going to pipe. And we're going to print out the test loss. And we want the test loss here. We're going to take this to 5 decimal places. Again, when we see the printouts of the different values, do not worry too much about the exact numbers on my screen appearing on your screen because that is inherent to the randomness of machine learning. So have we got, the direction is more important. Have we got, we need a percentage sign here because that's going to be a bit more complete for accuracy. Have we got any errors here? I don't know. We've just all coded this freehand, right? There's a lot of code going on here. So we're about to train our next model, which is the biggest model we've built so far in this course. 3 layers, 10 hidden units on each layer. Let's see what we've got. 3, 2, 1, run. Oh, what? What? 1,000 epochs, an extra hidden layer, more hidden units, and our model is still basically a coin toss. 50%. Now, this can't be for real. Let's plot the decision boundary. Plot the decision boundary. To find out, let's get a bit visual. Plot figure. Actually, to prevent us from writing out all of the plot code, let's just go up here and we'll copy this. Now, you know I'm not the biggest fan of copying code, but for this case, we've already written it, so there's nothing really new here to cover. And we're going to just change this from model 0 to model 1 because why? It's our new model that we just trained. And so behind the scenes, plot decision boundary is going to make predictions with the target model on the target data set and put it into a nice visual representation for us. Oh, I said nice visual representation. What does this look like? We've just got a coin toss on our data set. Our model is just, again, it's trying to draw a straight line to separate circular data. Now, why is this? Our model is based on linear. Is our data non-linear? Maybe I've revealed a few of my tricks. I've done a couple of reveals over the past few videos, but this is still quite annoying, and it can be fairly annoying when you're training models and they're not working. So how about we verify that this model can learn anything? Because right now it's just basically guessing for our data set. So this model looks a lot like the model we built in section 01. Let's go back to this. This is the Learn Pytorch.io book. Pytorch Workflow Fundamentals. Where did we create a model? Model Building Essentials. Where did we build a model? Linear Regression Model. Yeah, here. And then .linear. But we built this model down here. So all we've changed from 01 to here is we've added a couple of layers. The forward computation is quite similar. If this model can learn something on a straight line, can this model learn something on a straight line? So that's my challenge to you is grab the data set that we created in this previous notebook. So data, you could just reproduce this exact data set and see if you can write some code to fit the model that we built here, this one here, on the data set that we created in here. Because I want to verify that this model can learn anything. Because right now it seems like it's not learning anything at all. And that's quite frustrating. So give that a shot and I'll see you in the next video. Welcome back. In the past few videos, we've tried to build a model to separate the blue from red dots, yet our previous efforts have proven futile. But don't worry, we're going to get there. I promise you we're going to get there. And I may have a little bit of inside information here, but we're going to build a model to separate these blue dots from red dots, a fundamental classification model. And we tried a few things in the last couple of videos, such as training for longer, so more epochs. We added another layer. We increased the...
Questions or want to chat with me? Let me just turn on my camera now that we have some viewers. Should work, hopefully. Oops, no. Yeah, there we go. Hey, thank you for coming into my stream.
hidden units because we learned of a few methods to improve a model from a model perspective, such as upgrading the hyperparameters, such as number of layers, more hidden units, fitting for longer, changing the activation functions, changing the learning rate. We haven't quite done that one yet, and changing the loss function. One way that I like to troubleshoot problems is I'm going to put a subheading here, 5.1. We're going to preparing data to see if our model can fit a straight line. So one way to troubleshoot, this is my trick for troubleshooting problems, especially neural networks, but just machine learning in general, to troubleshoot a larger problem, is to test out a smaller problem. And so why is this? Well, because we know that we had something working in a previous section. So 01 PyTorch workflow fundamentals, we built a model here that worked. And if we go right down, we know that this linear model can fit a straight line.
We have 31 more minutes for our halfway mark. Well, not exactly a halfway mark, but I'll consider it a halfway mark anyways.
So we're going to replicate a data set to fit a straight line to see if the model that we're building here can learn anything at all, because right now it seems like it can't. It's just tossing a coin to split between our data here, which is not ideal. So let's make some data. But yeah, this is let's create a smaller problem, one that we know that works, and then add more complexity to try and solve our larger problem. So create some data. This is going to be the same as Notebook 01.
Right now it's just
And I'm going to set up weight equals 0.7, bias equals 0.3. We're going to move quite quickly through this because we've seen this in module 1. But the overall takeaway from this is we're going to see if our model works on any kind of problem at all, or do we have something fundamentally wrong. Create data. We're going to call it X regression because it's a straight line and we want it to predict a number rather than a class. So you might be thinking, oh, we might have to change a few things of our model architecture. Well, we'll see that in a second. Dot unsqueeze. And we're going to go on the first dimension here, or dim equals 1. And Y regression, we're going to use the linear regression formula as well. Weight times X. X regression, that is, because we're working with a new data set here, plus the bias. So this is linear regression formula without epsilon. So it's a simplified version of linear regression, but the same formula that we've seen in a previous section. So now let's check the data. Nothing we really haven't covered here, but we're going to do a sanity check on it to make sure that what we're dealing with is not just a load of garbage, because it's all about the data in machine learning. I can't stress to you enough. That's the Data Explorer's motto, is to visualize, visualize, visualize. Oh, what did we get wrong here? Unsqueeze, did you notice that typo? Why didn't you say something?
I like how you
I'm
said
kidding. There we go. Okay, so we've got 100 samples of X.
It's like, you know, I don't know if you have ever been in a school club, but the mascot always has a motto. Sounds like a main character's motto. Engineers' main motto would be visualize, visualize, visualize. Right. Anyhow, let's just quickly do this. There we go. Our viewer count is finally increasing. Hey to whoever is viewing. Well, multiple people are viewing, so hi to all. Why are we yeah, why do we need to copy that comment? Let's just quickly go through this. And while regression, let's print out the first 5 elements from both. And what's the type here? It needs to be a equal symbol. We're not subtracting anything.
We've got a different step size here, but that's all right. Let's have a little bit of fun with this. And we've got one X value per Y value. It's a very similar data set to what we used before. Now, what do we do once we have a data set? Well, if we haven't already got training and test splits, we better make them. So create train and test splits. And then we're going to go train split. We're going to use 80% equals int 0.8 times the length of, or we could just put 100 in there, but we're going to be specific here. And then we're going to go X train regression, Y train regression equals, what are these?
Let's just use scikit-learn. Although, what's the function's name? Scikit-learn. Scikit-learn split train test, yeah. Oh, it's called train test split. See, test size. Yeah, there we go. So, import. Let's just do that. Import scikit. Who is it? Let's see. I'll just copy that statement from there. It's like spelled as a scalar, isn't it? Anyhow, so how do we split this? Yeah, that should do. We don't need a random state. Our test, we need to do a 80-20 split, meaning our test size should be 20%. We'll put point to that. Then we need to pass it our X regression and Y regression that we created before this. So let me do that. X regression, Y regression. Alright, that should be good enough. We should
Is equal? Well, we're going to go.
You know what, let's print all of this. we'll print all of this, and we'll also print their respective lengths. Let's see if I can have multiple cursors again on Google Colab. 2, 3, 4. Oh, no. Yeah, there we go. There we go. Yeah. I thought that was that was gonna result in an indentation error. I didn't notice that it was the parameters. Anyhow, let's scroll down. 80-20, 80-20. Yep, sounds about right and looks right too. Cool. We have our test
on X regression, and we're going to index up to the train split on X, and then for the Y regression, we're going to index up to the train split. Wonderful. And then we can do the same on the test, or creating the test data. Nothing really new here that we need to discuss. We're creating training and test sets. What do they do for each of them? Well, the model is going to hopefully learn patterns in the training data set that is able to model the testing data set. And we're going to see that in a second. So if we check the lengths of each, what do we have? Length, X train, regression. We might just check X train, X test, regression. What do we have here? And then we're going to go length, Y train, regression. Long variable names here. Excuse me for that. But we want to keep it separate from our already existing X and Y data. What values do we have here? 80-20, 80-20. Beautiful. So 80 training samples to 100 testing samples. That should be enough. Now, because we've got our helper functions file here, and if you don't have this, remember we wrote some code up here before to, where is it? To download it from the course GitHub, and we imported plot predictions from it. Now, if we have a look at helperfunctions.py, it contains the plot predictions function that we created in the last section, section 0.1. There we go, plot predictions. So we're just running this exact same function here, or we're about to run it. It's going to save us from retyping out all of this. That's the beauty of having a helperfunctions.py file. So if we come down here, let's plot our data to visually inspect it. Right now it's just numbers on a page, and we're not going to plot really any predictions because we don't have any predictions yet, but we'll pass in the train data is equal to X train regression, and then the next one is the train labels, which is equal to Y train regression, and then we have the test data, which is equal to X test regression, and then we have the test labels. Now I think this should be labels too. Yeah, there we go. Y test regression. It might be proven wrong as we try to run this function. Okay, there we go. So we have some...
Oh, he named it X train. He added regression to...
Yeah, there we go. Y test regression. Might be proven wrong as we try to...
So let's do the same. Let's just get rid of these or comment out those print statements. So X train data is X train regression, train labels. Not have to spell that right. It's going to be Y, not a capital Y, small y train regression. Then our test data is going to be X test regression, and then our test labels is going to be Y test regression.
run this function. Okay, there we go. So we have some training data and we have some testing data. Now, do you think that our model 1,
why is it like this though? I mean, maybe I didn't pass it right.
have some training data and we have some testing
Y test regression, X test regression,
data. Y test regression.
Y train regression, X train regression.
Might be proven wrong as we try to run this function. Okay, there we go. So we have some training data and we have some testing data. Now,
There's something wrong there. Train, test.
do you think that our model 1, if we have a look, what's model 1, could fit this?
Is it like this though? Maybe, let's go to our first and just copy the function. Maybe someone might have changed it on GitHub, resulted in a typo or an error or something. Yeah, let's define this. Oh, we went right into the correct page now, didn't we? So let's do that instead. Let's define that. Let's use that. Guess not. So probably something I did with oh, is it because extreme regression, x-test regression, because I'm using train test split. Yeah, I have a feeling that's probably it. For the time being, I'm just gonna stick to what what we have had before in that case. So test split, right? Test split is gonna be 80% of length of x regression.
And then we have
I'm gonna convert that to an integer so that we can slice that, so that indentation slicing works correctly. X-train, Y-train, X-train regression and Y-train regression. Is gonna be the same thing, but we're gonna specify the what's it? Yeah, it should go only till the train split. We should get however many entries, 80% of the ranges. What happened here though? And this do the same thing, but we're gonna split forwards now. That should work, although it's giving me some type of error. Oh yeah, it's not train regression, it's supposed to be X regression. Supposed to be Y regression. Y regression, it's like asking a question. Let's name it train split. Although that is, no, it is the train split, isn't it? Okay, anyhow. Boom, boom, boom. That works, that works. So it might be because scikit-learn just randomizes the test and the other split, right?
test data, which is equal to x test regression, and then we have the test labels. Now I think this should be labels too. Yeah, there we go. Y test regression. It might be proven wrong as we try to run this function. Okay, there we go. So we have some training data and we have some testing data. Now, do you think that our model 1, if we have a look, what's model 1, could fit this data? Does it have the right amount of in and out features? We may have to adjust these slightly. So I'd like you to think about that. Do we have to change the input features to our model for this data set? And do we have to change the out features of our model for this data set? We'll find out in the next video. Welcome back. We're currently working through a little side project here. But really, the philosophy of what we're doing, we just created a straight line data set because we know that we've built a model in the past, back in section 01, to fit a straight line data set. And why are we doing this? Well, because the model that we've built so far is not fitting or not working on our circular data set here, on our classification data set. And so one way to troubleshoot a larger problem is to test out a smaller problem first. So later on, if you're working with a big machine learning data set, you probably start with a smaller portion of that data set first. Likewise, with a larger machine learning model. Instead of starting with a huge model, you'll start with a small model. So we're taking a step back here to see if our model is going to learn anything at all on a straight line data set so that we can improve it for a non-straight line data set. And there's another hint. Oh, we're going to cover it in a second, I promise you. But let's see how now we can adjust model 1 to fit a straight line. And I issued you the question at the end of the last video. Do we have to adjust the parameters of model 1 in any way, shape or form to fit this straight line data? And you may have realized, or you may not have, that our model 1 is set up for our classification data, which has 2x input features. Whereas this data, if we go X, train regression, how many input features do we have if we just get the first sample? There's only one value. Or maybe we get the first 10. There's only one value per, let's remind ourselves, this is input and output shapes, one of the most fundamental things in machine learning and deep learning. And trust me, I still get this wrong all the time, so that's why I'm harping on about it. We have one feature per one label, so we have to adjust our model slightly. We have to change the in features to be 1 instead of 2. The out features can stay the same because we want one number to come out. So, what we have to change the in features to be 1 instead of 2. The out features can stay the same because we want one number to come out. So, what we're going to do is code up a little bit different version of model 1. So, same architecture as model 1, but using nn.sequential. We're going to do the faster way of coding a model here. Let's create model 2, and nn.sequential. The only thing that's going to change is the number of input features. So this will be the exact same code as model 1, and the only difference, as I said, will be features, or in features is 1, and then we'll go out features equals 10, so 10 hidden units in the first layer, and of course the second layer, the number of features here has to line up with the out features of the previous layer. This one's going to output 10 features as well, so we're scaling things up from 1 feature to 10 to try and give our model as much of a chance or as many parameters as possible. Of course, we could make this number quite large. We could make it 1,000 features if we want. But there is an upper bound on these things. And I'm going to let you find those in your experience as a machine learning engineer and a data scientist. But for now, we're keeping it nice and small so we can run as many experiments as possible. Beautiful, look at that. We've created a sequential model. What happens with nn.sequential? Data goes in here, passes through this layer. Then it passes through this layer. Then it passes through this layer. And what happens when it goes through the layer? It triggers the layer's forward method, the internal forward method. In the case of nn.linear, we've seen it. It's got the linear regression formula. So if we go nn.linear, it performs this mathematical operation, the linear transformation. But we've seen that before. Let's keep pushing forward. Let's create a loss and an optimizer. Loss.
Features gonna be 10, out features gonna be 1. Gonna send that to our device, making device agnostic code here. That's quite a mouthful.
And optimize. We're going to work through our workflow. So loss function, we have to adjust this slightly. We're going to use the L1 loss because why? We're dealing with a regression problem here rather than a classification problem. And our optimizer, what can we use for our optimizer? How about we bring in just the exact same optimizer, SGD, that we've been using for our classification data. So model 2.params or parameters. I always get a little bit confused. And we'll give it an LR of 0.1 because that's what we've been using so far. This is the params here. So we want our optimizer to optimize our model 2 parameters here with a learning rate of 0.1. The learning rate is what? The amount each parameter will be, or the multiplier that will be applied to each parameter each epoch. So now, let's train the model. Do you think we could do that in this video? I think we can. So we might just train it on the training data set, and then we can evaluate it on the test data set separately. So we'll set up both manual seeds, CUDA, and because we've set our model to the device up here, so it should be on the GPU or whatever device you have active. So set the number of epochs. How many epochs should we set? Well, we set 1,000 before, so we'll keep it at that. Epochs equals 1,000, and now we're getting really good at this sort of stuff here. Let's put the data on the target device. And I know we've done a lot of the similar steps before, but there's a reason for that. I kept all these in here because I'd like you to buy...
Finally, we have our first chat of the day. We have it from, what's it? Poweropa. Hey there, how are you?
The end of this course is to sort of know
Alright,
all of this stuff off by heart.
You know, feel free to ask me any questions or anything that you have here. Okay. Let me get back to this. I'm fine, thanks. Alright, that's good. How come you found this stream? Just browsing through Twitch or? Epochs. I am PHP programmer, want to learn. Oh, I assume you meant ML. That's that's pretty cool. I myself am a Python programmer, Python developer. I used AutoGPT from GitHub. What is AutoGPT? I'm hearing that for the first time. AutoGPT. Oh, is this the one? AutoGPT is a vision of accessible AI for everyone to use. I'm coming across this for the first time. There is another similar like a tool or thing on GitHub though. It's called GPT for all. You might wanna look into that. Same concept, I believe. Like you can run these things in your own machine. The code for ChatGPT you can run on your laptop. You might mean like an LLM that can run on your system, right? Yeah, same thing. You might want to look into this GPT-4 all too. They have a it's pretty much the same thing. You don't need an OpenAI key or anything like that. You can run it on your own system. Have you built anything? Do you mind sharing your GitHub? I would be, glad to go through it. Are you a working professional by chance?
And even if you don't know it all off by heart, because trust me, I don't, you know where to look. So X-Train.
Extreme regression. Oh, and are you like a working professional by chance? Do you work right now? Are you a student? Like, what are you doing right now? Are you just studying? And yeah, if you can share your GitHub, I would be happy to go through it, see what all projects you have made and stuff. I make websites with PHP and Drupal. I'm not much of a PHP dev myself. Although I do know that PHP is used to power 60% of the web also. Have to confirm this stat, mainly from WordPress. Hearing Drupal for the first time. What is Drupal? Drupal. It's a module or something on PHP. That's pretty good. Flexible open source content management system. Oh, alright, gotcha. Thank you for answering that. I mean, what have you you're trying to convert into a machine learning role, right? Are you learning Python then for that?
Train regression, we're going to send this to device, and then we're going to go Y, train regression. Just a reminder, or something to get you to think.
I want to run. Again, key. Is it key or ML? What is KI? Did you make a typo there? I think you meant machine learning, right? Yeah, you have to use sorry, AI. Oh, okay, alright, gotcha. Yeah. KI in German. I didn't know AI was called KI in German. Oh, you might be messing with me. But yeah, great. Yeah, you have to. Technically, if you just want to use AI, yeah, there are plenty of options out there. You can just download GPT for all and maybe just run it if you just wanna have your own GPT clone. But if you wanna learn machine learning as such, you wanna really get into it, then yeah, you need to go into you need to learn Python like AutoGPT. Yeah, GPT for all. You know what? I'll can I paste in the link? I'll just let me just see if I can paste in the link. Oh, you know what? I believe I just need to go into twitch.tv, search for my name, and oops, not the code. Oops, not the code. Weird seeing myself. Not the code. Weird. Yeah, it I think it's pretty much like AutoGPT. I haven't used AutoGPT, but here in this about section makes me think so. What's this video?
Setting up and running the AutoGPT server and builder. This tutorial will cover downloading the necessary files. Navigate to the AutoGPT directory. Enter command to finish before running the next one. Run app in this folder. In your terminal, run the following commands. Once the front end is running, click the link to navigate to local and click run. Check your terminal window. Your server has received the request, is processing it, and has executed it. You successfully set up and tested AutoGPT.
I think it's pretty much like it. Here they provide API which you can use apparently locally. But yeah, I think it should be pretty similar. All the best in your machine learning journey, by the way.
while we're writing this code. What would happen if we didn't put our data on the same device as a model? We've seen that error come up before, but what happens? Well, I've just kind of given it away, haven't you, Daniel? Wow, that was a great question. Our code will error. Oh, well, don't worry. There's plenty of questions I've been giving you that I haven't given the answer to yet.
Yeah, with UI, that's right. It's just, yeah, you get a UI like how you would if you were to visit the GPT website. Although you need to make sure you have the correct specifications and everything needed, you know, to run it. Alright, let's currently I am kind of in the middle of checking if the model that I've created, or troubleshooting the binary class model that I've created on this tutorial. It's a, you know, I would recommend you start with this tutorial, Pytorch for deep learning and machine learning. It's a awesome tutorial from what I've experienced so far, to say the least. The link is like, if you go in my about section, you'll find the link to the video. Okay, so we're just sending the data sets to our device, making it device agnostic. Sounds like a code, but yeah, same thing for the test data sets too. Then I guess it will just be the training loop. Like
Device, beautiful. We've got a device agnostic code for the model and for the data. And now let's loop through epochs. So train, we're going to for epoch in range epochs for an epoch and a range. Do the forward pass. Calculate the loss. So ypred equals model 2. This is the forward pass. Xtrain, regression. It's all going to work out hunky-dory because our model and our data are on the same device. Loss equals what? We're going to bring in our loss function. We're going to compare the predictions to ytrain regression, to the y labels. What do we do next? Optimize a zero grad. Optimizer.zeroGrad. We're doing all of this without comments. Look at us go. Loss backward, and what's next? Optimizer step, step, step. And of course, we could do some testing here. Testing. We'll go model2.eval, and then we'll go with torch.inference mode. We'll do the forward pass. We'll create the test predictions equals model2.xtest regression. And then we'll go the test loss equals loss fn on the test predictions and versus the y test labels. Beautiful. Look at that. We've just done an optimization loop, something we spent a whole hour on before, maybe even longer, in about 10 lines of code. And of course, we could shorten this by making these a function. But we're going to see that later on. I'd rather us give a little bit of practice while this is still a bit fresh. Print out what's happening. Let's print out what's happening. What should we do? So because we're training for 1,000 epochs, I like the idea of printing out something every 100 epochs. That should be about enough of a step. Epoch, what do we got? We'll put in the epoch here with the f string, and then we'll go to loss, which will be loss, and maybe we'll get the first 5 of those, 5 decimal places that is. We don't have an accuracy, do we? Because we're working with regression. And we'll get the test loss out here, and that's going to be 0.5f as well. Beautiful. Have we got any mistakes? I don't think we do. We didn't even run this code cell before. We'll just run these 3 again, see if we got... Look at that. Oh my goodness. Is our loss is going down. So that
let's run this. That's a very big typo. So this needs to be white red and white train regression. Do it. Yep.
means our model must be learning something. Now, what if we adjusted the learning rate here? I think if we went 0.01 or something, will that do anything? Oh yes, look how low our loss gets on the test. Data set, but let's confirm that. We've got to make some predictions. Or maybe we should do that in the next video. Yeah, this one's getting too long, but how good's that? We created a straight line data set, and we created a model to fit it. We set up a loss and an optimizer already, and we put the data on the target device. We trained and we tested, so our model must be learning something. But I'd like you to give a shot at confirming that by using our plot predictions function. So make some predictions with our trained model. Don't forget to turn on inference mode, and we should see some red dots here, fairly close to the green dots on the next plot. Give that a shot, and I'll see you in the next video. Welcome back. In the last video, we did something very exciting. We solved a smaller problem that's giving us a hint towards our larger problem. So we know that
Just inverts the camera, so I'm just gonna go back. Just gonna exit out of that. At this rate, I need a cooler for my phone. Cooler for my phone or something like that.
the model that we've previously been building, Model 2, has the capacity to learn something. Now, how did we know that? Well, it's because we created this straight line data set. We replicated the architecture that we used for Model 1. Recall that Model 1 didn't work very well on our classification data, but with a little bit of an adjustment, such as...
Oh, now we have a second viewer on our channel yet again. Hey, to us watching, I just turned my camera off since my phone was getting a bit hot. I'll turn it back again. You know, feel free to ask me any questions. Oh, the video is very loud. Oh, it's power up again. 1 second, let me just turn this on. I'll just come back. Yeah, what was it? The video is very loud and your voice is low, huh? That's something I need to look into. Let me adjust this one. Thank you for telling me that. I'll check out what's happening. Although, why can't I adjust this? Can you lower your YouTube loudness? Yeah, you know what? Let's test this right now. You tell me if this is good enough. Let this play through. I'm just gonna speak.
changing the number of in features, and not too much different training code except for a different loss function because, well, we use MAE loss with regression data, and we changed the learning rate slightly because we found that maybe our model could learn a bit better. And again, I'd encourage you to play around with different values of the learning rate.
I have a feeling it might be okay, do not affect. Oh, it doesn't affect much now?
In fact, anything that we change, try and change it yourself and just see what happens. That's one of the best ways to learn what goes on with machine learning models. But we trained for the same number of epochs, we set up device agnostic code, we did a training and testing loop. Look how good this looks.
So that's bad. How about we come in here? I haven't altered the audio properties here. Let's I could swear I'd said this before decibels. What happened? That should be wait a second, let me turn on the video.
Oh my goodness, well done. And our loss went down. So, what does that tell us? Well, it tells us that Model 2, or the specific architecture, has some capacity to learn something. So, we must be missing something. And we're going to get to that in a minute, I promise you. But we're just going to confirm that our model has learned something. It's not just numbers on a page going down.
So what should we... Well, what we can do is, how about we turn off... Not turn off, I mean... What do these things even do? I'm actually changing obvious settings for the first time. Let's set that to -5 decibels. Maybe that way I'll still hear the sound, but you'll just hear my voice instead.
By getting visual. So, turn on We're going to make some predictions and plot them, and you may have already done this
is
because
it
you should have
better
challenged
now?
it last
Can you hear
at the end of the
me,
last video.
or-
So turn on evaluation
Oh,
mode.
look at
Let's
that.
go model 2
Our
dot
viewer
eval,
count is also
and
increasing.
let's make predictions, which are also known as inference.
It's, I
And we're going to go
read
with
it,
torch
but,
dot inf.
you know, let me hear myself. Much better. Ah, there we go.
Inference mode.
Thank you. You know,
Inference
I didn't realize that you guys weren't able to hear me. Thank you, Aparopa. But your voice should be louder. Like my actual voice or my something to do with my mic. You know what? Let's go in here, see if we can alter the properties. Okay, in that case, let's go to properties, advanced audio properties, and then change this from 4 to 8. I'm not sure what this does, to be frank.
Mode. Torch dot inference mode. Make some predictions. We're going to save them as y preds, and we're going to use model 2, and we're going to pass it through x.
Oh, this way? Not desktop down, not micro up, it will disturb. Didn't get what you're trying to tell me. Turn. Make the sound for desktop lower. Oh, okay, gotcha. Yeah. In that case, let me just return this back to what it was. Let's make this 4 and make this. Oops, why can't I make it 4? And make this, say, negative 10. Alright, let's give that a shot. Negative 10. Alright, let's do some testing now. Oops.
Test regression. This should all work as we've set up device agnostic code.
Should be
Plot data
better
and predictions.
now.
To do this, we can first use our plot
Okay,
predictions function
perfect.
that we imported via our helper function.
And I
Plot
can
function.
hear you
The code for that
just
is just a few
fine
cells
too.
above if you'd like to check that out.
So yeah,
But
should
let's
be
set up the
fine.
train data here.
Thank you,
Train data parameter,
Paropa.
which is X-train regression.
For I hope, is that your? Well, obviously that's not your real name, but am I pronouncing that the way it's supposed to be? Pavropa. Okay. Let's go back then.
Numbers on a page going down.
It's the emoji is very tiny. Wow, you are a streamer yourself, I believe then, if you have a... Are you a streamer yourself by chance?
By getting visual. So turn on. We're going to make.
You are a streamer yourself? Okay, I have to check this out. How I program. You can see some videos. Let's check that out. You made a Twitch bot, okay. Let's go to my Twitch account. For playing in the chat here with... maybe I need to go to my chat and then... for playing in the chat with the play command. Okay, alright. How did you create it? I haven't created any... The only bot I've created is for like Telegram. I don't know how to make a bot on Twitch. Did you create that with PHP itself? Let me just like my camera is just tilted, right? That should be better. So what were we about to do? Some videos show the game in the background. Or is this your like channel emoji? Alright. 4 years ago, okay. Oh, is this you there? The commands are...
Praxter 9, okay.
Alright. On the board, about bottom left. Maybe I'm looking at the wrong place. Bottom left is the game. Let me just make this full screen first of all, and bottom left. Maybe I'm in the wrong. Am I in the wrong section? Huh. Oh, okay. Is this German, by the way? So if I put what's it? Play, right? Maybe it's something else that I need to do. Maybe I did that wrong. Is that correct? Bot is not on. Okay, gotcha. So what exactly does this do? Though? I mean I can't of course read German. Um, like what is this game about? Gamble timer, text to speech. Look at the video. You made a video where you see the game. Okay, gotcha. Which video is that? Is that in here? Twitch clip. This one. This one. Which one should I view? Clap. Alright. Alright. Wait, what happened there? Okay, you did indeed make this on PHP. PHP Wizard. But the game is working and I am programming. You killed a fly, okay? Alright. Yeah. This is the game, anyways. Like the numbers are increasing and decreasing. Like I don't understand what is the game though. 625. Like the numbers just keep on going up, and it's like a game on the like the stock market, like with the horses and the balls, you know. Oh, okay, okay, like the things in carnival, right? Like you throw. I am just assuming. Is that what you're referring to? This game. Alright, let's see what that game is. Go back. Okay, yeah, the ones in carnival, right? Yeah. To play with the community. That is cool. How was your you have 166 followers, way more than me. Last live 4 years ago. Did you stop streaming then? By and you just do like you just focus your full time on programming. Yes, only on Corona. I see. So the pandemic was the time when you streamed. You know what? If you are like I don't know any one thing that I want to do in future is get into some hackathons. I don't know if they have that in Germany. Well, they don't have that in. They do have that in India, but it's like very rare. So if you wanna collab with me by chance, you know, I would appreciate that. Yeah. Although I don't have any. I haven't found any yet though. Just to clarify, so you're working right now, or are you? I assume you're working, right? Or sure. Haha, right. That's what I like to hear. There you go. Oh, what is this? 300 channel points. Is that a feature or something? Oh, like how you set up. Oh wait, what? Establishing connection. Oh, you just followed me. I heard a sound. Thank you for that. I need to set up. How do you unlock this bit? I did a Google search. You need some 50 followers or something, right? Oh, look at that. Our viewer count is increasing now. Seems like our conversation had some magic in it. Right. Hi to whoever's watching. I'm just having a conversation with one of my followers right now. Latest follower, in fact. Right, thank you, Pauropa. I'm gonna return to my stream now. It was a very good conversation that we had right now. Wish you all the best in your machine learning journey. Best in your machine learning journey. Best in your machine learning journey. You're nice. You go offline. Or are you trying to say, is it like a 24/7 stream or not? Are you asking me that? And why am I viewing my own stream? Let me go back. Are you asking me that? Is it a 24/7 stream?
Make some predictions and plot them.
Like, are you asking me whether I stream for 24 hours straight, like a marathon or something? I didn't understand the question. By, like, what did you mean by you go offline?
And you may have already done this because I issued that challenge at the end of the last video. So turn on evaluation mode. Let's go model2.eval, and let's make predictions, which are also known as inference. And we're going to go with torch.inference mode. Inference mode. With torch.inference mode. Make some predictions. We're going to save them.
Oh, no, sorry. No, I'm not going offline now. I still have yeah, let's go learning. I would be still streaming for maybe 30 minutes or so, 34 minutes or so. Yeah. Let's go, Mario.
Them as y preds, and we're going to use model 2, and we're going to pass it through x-test regression. This should all work because we've set up device agnostic code, plot data, and predictions. To do this, we can of course use our plot predictions function that we imported via our helper functions.py function. The code for that is just a few cells
look
above.
at that. Our predictions are in line with our wait, where is that red thing? Yeah. Oh, I didn't view this. Wait, which? Oh, I'm in a different collab right now.
Let's set up the train data here. Train data parameter, which is x-train regression, and
well, where exactly were we though? Yeah, so we found our lowest was
or this specific architecture has some capacity to learn something, so we must be missing something. And we're going to get to that in a minute, I promise you. But we're just going to confirm that our model has learned something, and it's not just numbers on a page going down by getting visual. So turn on, we're going to make some predictions and plot them, and you may have already done this because I issued that challenge at the end of the last video. So turn on evaluation mode. Let's go model2.eval, and let's make predictions, which are also known as inference. And we're going to go with torch.inference mode. Inference mode. With torch.inference mode. Make some predictions. We're going to save them as y threads, and we're going to use model 2, and we're going to pass it through x-test regression. This should all work because we've set up device agnostic code, plot data, and predictions. To do this, we can of course use our plot predictions function that we imported via our helper functions.py function. The code for that is just a few cells above if you'd like to check that out. But let's set up the train data here.
X-test regression, and then we're gonna plot that in.
Train data parameter, which is x-train regression, and my goodness, Google Colab, I'm already typing fast enough. You don't have to slow me down by giving me the wrong autocorrects. Train label equals y-train regression,
Sometimes the
and then we're going to
autocorrect
pass in our
doesn't
test
work
data,
correctly.
x-test regression, and then we're going to pass in test labels, which is y test regression. Got too many variables going on here, my goodness gracious. We could have done better with naming, but this will do for now. Is y preds, and then if we plot this,
Yeah.
what does it look like? Oh no, we've got an error. Now secretly, I kind of knew that was coming ahead of time.
The error can't convert. Oh yeah, we need to convert the tensors into. We need to send them back to CPU because NumPy doesn't support GPU apparently. So let's do that ahead of time before Daniel, our instructor here, shows us how to. So we have a test data, test labels. Gonna put in y test regression. Predictions is gonna be y.
Y preds, and then if we plot this, what does it look like? Oh no, we've got an error. With naming, but this will do for now. Is y preds.
Yeah, so the things that we need to change would be, actually wait a second, I wouldn't get that error because I'm not using the GPU anyhow, so guess that would just be Daniel's fault. Not Daniel's fault, I mean Daniel's problem, or yeah, anyhow. So yeah, there we go. Our predictions are almost in line with what they should actually be. So yeah, if we run this again, I mean if we train it again, that should, are they closer? Maybe they are closer.
Yes, what does it look like? Oh no, we've got an error.
Yeah.
Now,
Well, now this is good because you see, like if I had, you know what? Let me show it to you from the beginning. So when I create the model, let me just go to that. So here I'm just creating the model. I named it model 2 with these many layers. Now if I go down and I just train it for like 10 epochs. Epoch is basically a training loop. The higher number of epochs you have, the more it would train itself. So if I have just 10 epochs, and then I go ahead and print out what my model has learned till now. You see the predictions it has made are just absolute garbage, to be frank. Like this, the red indicates the predictions that the model has made, and this is what it should have been. Now yeah, it's very bad with 10 epochs. So if I increase that to 1000 and run that and plot it again. Hey, wait, what happened? Oh, sorry, I guess I need to run the loss function again. Yeah, 1000 is better, but one second, I'll get back. Yeah, so it's much closer now. So it's more epoxy solution. In this case, yeah, I guess increasing more epochs would result in a better result, ironically. Now, okay, so 1000 is still better but not correct. I mean, in machine learning, there isn't really, nothing is correct, right? It's all probabilistic. We get it as far as we can. So let's just try that out. If we increase that to 1000, that's taking up some space there. Yeah, that is more closer, right? It's more closer there. So in videos, more training will result in better results. Not always. There are a lot of, at least from what I've understood so far, there are a lot of variables out there. Like the type of layer that you're using matters. So in here I've used, where's my model definition? Go. So here I've used the linear layer, right? And it's the number of layers and the type of layer that I use also matters. So if I add more layers, I might get better results because there are more numbers to crunch. Similarly, the number of features that I give also matters. Another thing which matters is the loss function that I use. Here I am using a loss function called mean absolute error. Basically, if you see here, this loss value as such is decreasing, and that's a good thing, because the closer the loss gets to 0, the higher it reaches here. Loss is just basically the difference between the distance of the green and red points. There's a super good YouTube channel called 2-Minute Papers. He's a science for ray tracing and showing the state of the art with the 2-Minute Papers. Have I heard of that meme before? I think I have. You know what? Since you now I want to check it out. That 2-minute papers.
OpenAI built a
Oh, are they are an AI centric channel, huh? AI is evolving constantly, like everything with channel. You love this channel, huh? It's cool. And I'll definitely check it out in my free time. Now that's the thing I love about AI. We are literally like living in the AI rush. I myself don't know much about it, at least yet, but I'm learning on a daily basis. I want to become a ML expert. Expert in software development as such.
Secretly, I kind of knew that was coming ahead of time. That's the advantage of being the host of this.
But yeah, anyway, my point is, lot of variables involved, to put it short, not just the number of epochs.
So type error, how do we fix this? Remember how I asked you in one of the last videos what would happen if our data wasn't on the same device as our model? Well, we'd get an error, right? But this is a little bit different as well. We've seen this one before. We've got CUDA device type tensor to numpy. Where is this coming from? Well, because our plot predictions function uses matplotlib, and behind the scenes, matplotlib references numpy, which is another numerical computing library. However, numpy uses a CPU rather than the GPU. So we have to call .cpu, this helpful message is telling us, call tensor.cpu before we use our tensors with numpy. So let's just call .cpu on all of our tensor inputs here, and see if this solves our problem. Wonderful, looks like it does. Oh my goodness, look at those red dots, so close. Well, okay, so this just confirms our suspicions. What we kind of already knew is that our model did have some capacity to learn. It's just the data set, when we changed the data set, it worked. So, is it our data that our model can't learn on? Like this circular data? Or is the model...
Of course, it's the circular data. There's no way you can use a linear line to separate between the red and blue dots.
itself? Remember, our model is only comprised of linear functions. What is linear? Linear is a straight line, but is our data made of just straight lines? I think it's got some non-linearities in there. So, the big secret I've been holding back will reveal itself starting from the next video. So if you want a head start on it, I'd go to Torch NN, and if we have a look at the documentation, we've been speaking a lot about linear functions. What are these? Non-linear activations. And I'll give you another spoiler. We've actually seen one of these non-linear activations throughout this notebook. So go and check that out, see what you can infer from that, and I'll see you in the next video. Let's get started with non-linearities. Welcome back. In the last video, we saw that the model that we've been building has some potential to learn. I mean, look at these predictions. You could get a little bit better, of course, get the red dots on top of the green dots, but we're just going to leave that. The trend is what we're after. Our model has some capacity to learn, except this is straight line data. And we've been hinting at it a fair bit, is that we're using linear functions. And if we look up linear data, what does it look like? Well, it has quite a straight line. If we go linear, we just search linear. What does this give us? Linear means straight. There we go, straight. And then what happens if we search for non-linear? I kind of hinted at this as well. Non-linear. Oh, we get some curves. We get curved lines. So linear functions, straight, non-linear functions. Now, this is one of the beautiful things about machine learning. And I'm not sure about you, but when I was in high school, I kind of learned a concept called line of best fit, or y equals mx plus c, or y equals mx plus b, and it looks something like this. And then if you wanted to go over these, you use quadratic functions and a whole bunch of other stuff. But one of the most fundamental things about machine learning is that we build neural networks. And deep down, neural networks are just a combination, it could be a large combination of linear functions and non-linear functions. So that's why in torch.nn, we have non-linear activations and we have all these other different types of layers. But essentially what they're doing deep down is combining straight lines with, we go back up to our data, non-straight lines. So of course our model didn't work before because we've only given it the power to use linear lines. We've only given it the power to use straight lines. But our data is what? it's curved. Although it's simple, we need non-linearity to be able to model this data set. And now, let's say we were building a pizza detection model. So let's look up some images of pizza, one of my favorite foods. Images. Pizza, right? So could you model pizza with just straight lines? Now you're thinking, Daniel, you can't be serious. A computer vision model doesn't look for just straight lines in this. And I'd argue that, yes, it does, except we also add some curved lines in here. That's the beauty of machine learning. Could you imagine trying to write the rules of an algorithm to detect that this is a pizza? Maybe you could put in, oh, it's a curve here, and if you see red, and no. Imagine if you're trying to do 100 different foods. Your program would get really large. Instead, we give our machine learning models, we come down to the model that we created, we give our deep learning models the capacity to use linear and non-linear functions. We haven't seen any non-linear layers just yet. Or maybe we've hinted at some, but that's all right. So we stack these on top of each other, these layers, and then the model figures out what patterns in the data it should use, what lines it should draw to draw patterns through not only pizza, but another food such as sushi. If we wanted to build a food image classification model, it would do this. The principle remains the same. So the question I'm going to pose to you, we'll get out of this, is we'll come down here. We've unlocked the missing piece, or we're about to. We're going to cover it over the next couple of videos. The missing piece of our model. And this is a big one. This is going to follow you throughout all of machine learning and deep learning. Non-linearity. So the question here is, what patterns could you draw if you were given an infinite amount of straight and non-straight lines?
What patterns could you draw, Shiva? I mean, everything in the world, right?
Or in machine learning terms, an infinite amount, but really it is finite. By infinite, in machine learning terms, this is a technicality. It could be a million parameters. It could be, as we've got, probably 100 parameters in our model. So just imagine a large amount of straight and non-straight lines, an infinite amount of linear and non-linear functions. You could draw some pretty intricate patterns, couldn't you? And that's what gives machine learning, and especially neural networks, the capacity to not only fit
all the patterns in the world, I might argue,
straight line here, but to separate two different circles, but also to do crazy things like drive a self-driving car, or at least power the vision system of a self-driving car. Of course, after that, you need some programming to plan what to actually do with what you see in an image. But we're getting ahead of ourselves here. Let's now start diving into non-linearity. And the whole idea here is combining the power of linear and non-linear functions. Straight lines and non-straight lines. Our classification data is not comprised of just straight lines, it's circles. So we need non-linearity here. So recreating non-linear data, red and blue circles. We don't need to recreate this, but we're going to do it anyway for completeness. So let's get a little bit of a practice. Make and plot data. This is so that you can practice the use of nonlinearity on your own. Matplotlib.pyplot as PLT. We're going to go a bit faster here because we've covered this code above. So import make circles. We're just going to recreate the exact same circle data set that we've created above. Number of samples, we'll create 1,000. And we're going to create x and y equals what? Make circles, pass it in number of samples. Beautiful. Colab, please. I wonder if I can turn off autocorrect in Colab. I'm happy to just see all of my errors in the flesh. Look at that. I don't want that. I want noise like that. Maybe I'll do that in the next video. We're not going to spend time here looking around how to do it. We can work that out on the fly later. For now, I'm too excited to share with you the power of nonlinearity. So here, x, we're just going to plot what's going on. We've got two x features, and we're going to color it with the flavor of y, because we're doing binary classification. And we're going to use one of my favorite C maps, which is color map, and we're going to go plt.cm for C map, and red, blue. What do we get? Okay, red circle, blue circle.
Add a bit of noise there. And for reproducibility, I'm gonna use 42. Right? Who typed in non-local there? Autocorrect is a bit weird on Colab. Anyhow, loaded scatter x. Red and blue, and run. That's not a circle. Number of samples. I didn't define this. Maybe use it from the previous code blocks. Anyhow. Make circles, number of samples, noise, we put in too much noise there. It's 0.03 that we need to put in. There you go.
Hey, is that the same color as what's above?
Better.
I like this color better. Did we get that right up here? Oh my goodness, look how much code we've written. Yeah, I like the other blue. I'm going to bring this down here. It's all about aesthetics in machine learning. It's not just numbers on a page. How could you be so crass? Let's go there. Okay, that's a better color, red and blue. That's more lively, isn't it? So now let's convert to train and test, and then we can start to build a model with nonlinearity. Oh, this is so good. Okay, convert data to tensors, and then to train and test splits. Nothing we haven't covered here before. So import torch, but it never hurts to practice code, right? import torch from sklearn.model selection, import train test split so that we can split our red and blue dots randomly, and we're going to turn data into tensors, and we'll go x equals torch from numpy, and we'll pass in x here, and then we'll change it into type torch.float. Why do we do this? Well, because, oh my goodness, autocorrect. It's getting the best of me here. You're watching me live code this stuff and battle with autocorrect. That's what this whole course is. Am I really teaching Pytorch, or am I just battling with Google Colab's autocorrect? We are turning it into torch.float because why? NumPy is default, which is what makes circles users behind the scenes. NumPy is actually used in a lot of other machine learning libraries. Pandas.
Okay, let's do this. Converting that into
Because why? NumPy is default, which is what makes circles
tensors.
users behind the scenes. NumPy is actually used in a lot of other machine learning libraries. Pandas, built on NumPy. Scikit-learn does a lot of NumPy. Matplotlib, NumPy. That's just showing the, what's the word? Is it ubiquitous? Ubiquity? I'm not sure, maybe. If not, you can correct me. The ubiquity of NumPy. And test sets, but we're using Pytorch to leverage the power of autograd, which is what powers our gradient descent, and the fact that it can use GPUs. So we're creating train and test splits here with train test split, x, y, and we're going to go test size equals 0.2, and we're going to set random state equals 42, and then we'll view our first 5 samples. Are these going to be tensors? Fingers crossed, we haven't got an error. Beautiful, we have tensors here. Okay, now we're up to the exciting part. We've got our data set back.
Yeah, hold on a second. X, Y. So basically we're gonna make wait, train test split, yeah, 20%, so that's why we put 0.2 there. For reproducibility, we're gonna set the random state to 42.
Fingers crossed, we haven't got an error. Beautiful, we have tensors here. Okay, now we're up to the exciting part. We've got our data set back. I think it's time to build a model with nonlinearity. So if you'd like to peek ahead, check out TorchNN again. This is a little bit of a spoiler. Go into the nonlinear activation, see if you can find the one that we've already used. That's your challenge. Can you find the one we've already used? And go into the nonlinear activation, see if you can find the one that we've already used.
We've already used. What does it mean by that? So we have already used linear layers, of course, and I mean we've only used that so far. Yeah, we've only used that.
Use. That's your challenge.
Close.
Can you find the one we've already used?
The
And go into
tabs
here
over there.
and search what is a non-linear function. So give that a go and see what comes up. I'll see you in the next video.
Any function that's
Welcome
not a
back.
straight
Now,
line.
put your hand up if you're ready to learn about non-linearity. And I know I can't see your hands up, but I better see some hands
Yep.
up, or I better feel some hands up, because my hands up, because
Well,
non-linearity
Chad
is
can see my
a magic
hands up.
piece of the puzzle that we're about to learn about. So let's title this section, Building a Model with Non-Linearity. So just to re-emphasize, linear equals straight lines, and in turn, non-linear equals non-straight lines. And I left off the end of the last video, giving you the challenge of checking out the torch.nn module, looking for the non-linear function that we've already used. Now, where would you go to find such a thing? And, oh, what do we have in here? Non-linear activations. And there's going to be a fair few things here, but essentially all of the modules within torch.nn are either some form of layer in a neural network, if we recall. Let's go to a neural network. We've seen the anatomy of a neural network. Generally, you'll have an input layer and then multiple hidden layers and some form of output layer. Well, these multiple hidden layers can be almost any combination of what's in torch.nn, and in fact, they can almost be any combination of function you could imagine. Whether they work or not is another question. But Pytorch implements some of the most common layers that you would have as hidden layers, and they might be pooling layers, padding layers, activation functions, and they all have the same premise. They perform some sort of mathematical operation on an input. And so
I have 3 layers. For this model, yeah, I do have 3 layers as is defined in this one. You know, it's yesterday there was a TensorFlow playground. That's one. So this is what layer is. It's really cool. So yeah, exactly. You can just play around with this to get a sense. So it would be like we have 3 layers. first there's just it goes, there's only 1 here, it goes into 10, then it takes 10 in here, then it again outputs 10, then there's another layer which just combines everything and then puts it into 1. I hope that makes sense. That's a bit of a mouthful.
We look into the non-linear activation functions. You might have found nn.sigmoid. Where have we used this before? There's a sigmoid activation function in math terminology. It takes some input x, performs this operation on it, and here's what it looks like if we did it on a straight line. But I think we should put this in practice. And if you want an example, well, there's an example there. All of the other non-linear activations have examples as well, but I'll let you go through all of these in your own time. Otherwise, we're going to be here forever. nn.relu is another common function. We saw that when we looked at the architecture of a classification network. So with that being said, how about we start to code a classification model with non-linearity? And of course, if you wanted to, you could look up what is a non-linear function if you wanted to learn more. Non-linear means the graph is not a straight line. Oh, beautiful. So that's how I learned about non-linear functions. But while we're here together, how about we write some
Mind
code?
blown.
So let's go build a model with non-linear activation functions. And just one more thing before, just to re-emphasize what we're doing here. Before we write this code, I just remembered, I've got a nice slide, which is the question we posed in the previous video, the missing piece, non-linearity. But the question I want you to think about is, what could you draw if you had an unlimited amount of straight, in other words linear, and non-straight, non-linear lines? So we've seen previously that we can build a model, a linear model to fit some data that's in a straight line, linear data. But when we're working with non-linear data, well, we need the power of non-linear functions. So this is circular data. And now, this is only a 2D plot, keep in mind there. Whereas neural networks and machine learning models can work with numbers that are in hundreds of dimensions. Impossible for us humans to visualize, but since computers love numbers, it's a piece of cake to them. So from Torch import NN, we're going to create our first neural network with non-linear activations. This is so exciting. So let's create a class here. We'll create circle model. We've got circle model v1 already. We're going to create circle model v2. And we'll inherit from nn.module. And then we'll write the constructor, which is the init function. And we'll pass in self here. And then we'll go self, or super, sorry. Too many S words. Dot underscore underscore init underscore. There we go. So we've got the constructor here. And now let's create a layer.
Oh, our viewer
self
count has
one
increased. Hey to whoever's watching the stream right now. Alright, let's code this model now. We can use sequential, right? Why do we need
just the same as what we've used before. nn.linear. We're going to create this quite similar to the model that before, except with one added feature. And we're going to create in features, which is akin to the number of x features that we have here. Again, if this was different, if we had feature. And we're going to create in features, which is akin to the number of x features that we have here. Again, if this was different, if we had 3x features, we might change this to 3. But because we're working with 2, we'll leave it as that. We'll keep out features as 10, so that we have 10 hidden units. And then we'll go layer 2. And then linear. Again, these values here are very customizable. Because why? Because they're hyperparameters. So let's line up the out features of layer 2. And we'll do the same with layer 3. Because layer 3 is going to take the outputs of layer 2, so it needs in features of 10, and we want layer 3 to be the output layer, and we want one number as output, so we'll set 1 here. Now, here's the fun part. We're going to introduce a non-linear function. We're going to introduce the ReLU function. Now, we've seen sigmoid. ReLU is another very common one. It's actually quite simple, but let's write it out first.
Hold on a second. Let me just go till here, and then I'll listen to what ReLU is. Just copy this line, and then just change this to 3. Change that to we'll output just 1
nn.relu.
One value, it's either true or false.
So remember, torch.nn stores a lot of existing nonlinear activation functions so that we don't necessarily have to code them ourselves. However, if we did want to code a ReLU function, let me show you, it's actually quite simple. If we dive into nn.relu, or ReLU, however you want to say it, I usually say ReLU, applies the rectified linear unit function element-wise. So that means element-wise on every element in our input tensor. And so it stands for rectified linear unit, and here's what it does. Basically, it takes an input. If the input is negative, it turns the input to 0, and it leaves the positive inputs how they are. And so this line is not straight.
Right.
You could argue, yeah, well, it's straight here and then straight there, but this is a form of a non-linear activation function. So it goes boom, boom. If it was linear, it would just stay straight there like that. But let's see it in practice. Do you think this is going to improve our model? Well, let's find out together, hey? Forward, we need to...
Let's find out indeed. ReLU, the LNU is rectified linear unit. Okay.
To implement the forward method. And here's what we're going to do. Where should we put our non-linear...
Why do you write code cannot copy? I can copy if I want to, but that wouldn't be learning. uh, with coding, you always have to type it out, even if it's right in front of you. If you're learning, if you are working, go ahead, copy it out, don't waste time. But initially, you have to, do this to learn. Alright, yeah, define the forward function. So the forward function is basically what happens when our model predicts numbers or predicts the output.
Activation functions. So I'm just going to put a note here. Relu is a nonlinear activation function. And remember, wherever I say function, it's just performing some sort of operation on a numerical input. So we're going to put a nonlinear activation function in between each of our layers. So let me show you what this looks like.
In between each of our layers. So I'm just going to predict this first. I guess if we put a relu in between each of our functions, it would look something like, well, first let's just call all the layers, all the linear layers. Great. And in between we put relu layer. It's got Daniel, the person teaching the tutorial, says. So let's do that. Is that what we are going for?
Layer 3. We're going to start from the outside in. Self.relu, and then we're going to go self.layer 2.
Viewer count has increased
and then we're going to go
again.
self.relu, and then there's a fair bit going on here, but nothing we can't handle. Layer 1, and then here's the x. So what happens is, our data goes into layer 1, performs a linear operation with nn.linear. Then we pass
Oh, there you go. I
the
predicted
output
it right.
of layer 1 to a relu function. So where's relu up here? We turn all of the negative outputs of our model, of layer 1 to 0, and we keep the positives how they are. And then we do the same here with layer 2. And then finally, the outputs of layer 3 stay as they are. We've got out features there. We don't have a relu on the end here, because we're going to pass the outputs to the sigmoid function later on. And if we really wanted to, we could put...
I just got so excited with the code, I didn't realize we're at the... not exactly the halfway mark, but halfway to 24 hours.
self.sigmoid here equals nn.sigmoid. But I'm going to... that's just one way of constructing it. We're just going to apply the sigmoid function to the logits of our model, because what are the logits? The raw output of our model. And so let's instantiate our model. This is going to be called model 3, which is a little bit confusing, but we're up to model 3, which is circle model v2, and we're going to send that to the target device. And then let's check model 3. What does this look like? Wonderful. So it doesn't actually show us where the relus are up here, but it just shows us what are the parameters of our circle model v2. Now, I'd like you to have a think about this, and my challenge to you is to go ahead and see if this model is capable of working on our data, on our circular data. So we've got the data sets ready. You need to set up some training code. My challenge to you is write that training code and see if this model works. But
Alright, let's do that.
we're going to go through that over the next few videos. And also, my other challenge to you is to go to the TensorFlow playground and recreate our neural network here. You can have 2 hidden layers. Does this go to 10? Well, it only goes to 8.
Let's, you know what? I'll be concluding the stream after I write the training loop, and we're almost on the 3-hour mark right now. So let me just quickly write the training loop, training and evaluation loop in features. Made a typo there, didn't I? Alright, so here's what I'm gonna do. Okay, this is why I write code. Now I have to remember what I learned. Okay, so what we're gonna do is we're gonna set the number of epochs. We're not going to make it device agnostic right now. We're just gonna keep everything as it is. So the epochs is 1000 for epoch, and range epochs for each training loop. What are we gonna do? We're gonna set our model into training mode. And what are we gonna do next? We're gonna, what should we do next? Calculate the loss, right? Well, first of all, let's get our predictions to the
So build something like this.
So model 3, we're gonna pass in our x tests, and we're gonna get our y logits first. Now remember, we are going to use we need to change our loss functions now. So for that, I'm gonna create a code block, set loss function. Why is my UPS acting up? I don't know if it's audible through the mic, but the fan is just, let me just check it out. It's a bit weird. Anyhow,
got two layers
so
of-
we have our no, yeah. So we need to set our loss function to be torch. Our loss function is going to be BC loss with logit, something like that. Binary cross entropy. That's what BC stands for. So torch dot neural network dot, yep, autocomplete, come up, there we go, PC with logits loss. And our we need an optimizer too. Optimizer is gonna be stochastic gradient descent, or SGD for short. GD. Wait, we have that. Oh wait, we have to define our parameters. So the parameters that you need to optimize would be from model 3. So model 3 dot parameters, and the learning rate, let's just do 0.01. Should be not enough. Alright, epochs for epoch. Now we get the logits. Now we're gonna convert the logits into labels by doing well, first of all, we're going to use our activation function, which is sigmoid in this case. We're going to pass in logits to it, and to convert that into the labels, or in fact, or in other words, is this a red dot or is this a blue dot? Ones or zeros, we're going to round it off. So we're going to use torch dot round on that. Okay. Then we'll use torch.round. Now what we're gonna do is we're gonna calculate the loss finally. So for doing that, loss is just loss function. We're gonna pass the y logits. Why the y logits, you ask? Because the activation is already done with BC with logits loss, so we don't need to activate it prior to that. And we're gonna compare that against our y training set, and then we're also gonna calculate our accuracy, which is gonna be, we're gonna call our accuracy function, and our ground truth is going to be set to y train. You know what, I'll just put this into the next line to make it more beautiful. And of course our y predictions is just gonna be y predictions. So we have loss, we have accuracy calculated. Now we're gonna use the zero grad method. Why? So that it doesn't accumulate the gradient for each of our weights and biases on and on. Next, what we're gonna do is we're gonna step our optimizer. Before that, we are gonna calculate our backward loss. This uses backpropagation. What else? Yeah, now time for the evaluation loop. So we're gonna set our model to eval mod, and then we're gonna open it up in torch.inference. And then we're gonna, what are we gonna do? With torch.inference mod, right? We're gonna train, and to train we need the test. You know, I'm just gonna copy this for now. Test logits. test predictions. Yep, X test. Should be X train, not X test. X train, Y train. X test, Y test. Test logits. This is gonna be test spread. And at last we this is gonna be test close, by the way, and we're gonna compare it with the test. We're also gonna calculate test accuracy, is what I was about to say. Y true is gonna be our Y test, and Y predictions is gonna be our test predictions. I'm gonna print everything, but before we do that, we're only gonna print every 100. Let's just print every 100th epoch. Gonna print what's happening. It's gonna copy the print statement from before. This doesn't have everything. The print statement before this. Yeah, there we go. Alright, and hopefully that works first try. Let's see. Nah, it did not work first try. Okay, it must be this. Okay, I forgot to you need to squeeze this down. To squeeze our predictions. Squeeze. Same here. That should work. Okay, now what? Still the same thing? What did I squeeze? I need to squeeze this, right? To squeeze the logits. Okay, I got excited too soon. So it rose and then it fell down. It's still the same, it's still the same. Maybe, you know what, let's just let's plot the, yeah, let's plot this. Moment of truth. That did not work.
5, it's a little bit different to ours because we've got 2 layers with 10. And then put the learning rate to 0.01. Or what do we have? 0.1 with stochastic gradient descent. We've been using 0.1, so we'll leave that. So this is the TensorFlow playground. And then change the activation here. Instead of linear, which we've used before, change.
Alright, you know what? I have reached the 3 minute, not the 3 minute, 3 hour mark. I'm gonna take a break for now, and then I'll catch you in the next stream. I don't know if I'm assuming is it Power Up House watching. I can see the viewer count as 2. Anyhow, before I leave, huge thank you to Power Up for sticking through. I really appreciate it if you're listening to this. Alright, cheers. I'm gonna end the stream now, and I'll catch you all in the next one. There we go. Alright, cheers, Power Up. Take care. Right. Bye to everyone.